Hi, this is bonding. It's going to be a binary unit, meaning two chapters. Chapter 7 is on ionic bonding, and then Chapter 8 is on covalent bonding. Ionic bonding is when you have a transfer of electrons, and covalent bonding is when you have a sharing. But there is a large gray area involved. Let's begin. Pyrite, FeS2, a common mineral that emits sparks when struck against steel, is often mistaken for gold, hence its name, fool's gold. Although certainly not worth its weight in gold, pyrite can be used as a source of sulfur in the production of sulfuric acid, a common industrial chemical. Pyrite is an example of a crystalline solid. In crystalline solids, the component particles of the substance are arranged in an orderly, repeating fashion. In this chapter, you will learn about crystalline solids composed of ions that are bonded together. But first, you need to understand how ions form from neutral atoms. This may not be worth its weight in gold, but it certainly was many, many years ago when they had to start fires easily. And here are some examples of crystalline solids, rocks, that can be used for weapons, cleave weapons and cooking and things around the house. Many, many, many years ago, you could form knives that could be used for daily chores very easily, or weapons against your implacable enemies. So the crystalline solids were very useful in the olden days. Mendeleev used similarities in the properties of elements to organize his periodic table. Scientists later learned that all of the chemicals within each group of the periodic table behave similarly because they have the same number of valence electrons. Valence electrons are the electrons in the highest occupied energy level of an element's atoms. The number of valence electrons largely determines the chemical properties of an element. The number of valence electrons is related to the group number in the periodic table. Well, not necessarily, because we're using the periodic table that the entire world uses, with the exception of the United States. So we're using the periodic table which is labeled 1 through 18. To find the number of valence electrons in an atom of representative elements, simply look at its group number. For example, the elements of group 1A, hydrogen, lithium, sodium, potassium, and so forth, all have 1 valence electrons, corresponding to the 1 in 1A. Carbon and silicon in group 4A have 4 valence electrons. Nitrogen and phosphorus in 5A have 5 electrons, and oxygen and sulfur in group 6A have 6. Well, all you have to do, really, if you're using the 1 through 18 periodic table, is look at the S&P positions that each element is in, and that will tell you the number of valence electrons. So it's really not necessary to understand what group they're in. The noble gases 8A or 18 are the only exception to the group number rule. Helium has 2 valence electrons, and all of the other noble gases have 8. Figure 1 on the next page shows some applications of group 4A elements. Valence electrons are usually the only electrons used in chemical bonds. Therefore, as a general rule, only the valence electrons are shown in electron dot structures. Electron dot structures are diagrams that show valence electrons as dots. Table 1, in 3 pages, shows electron dot structures for atoms of some group A elements. Now just make sure that you can draw the connection between group A elements and the elements that are listed 1 through 18. Figure 1. Group 4A elements include carbon, silicon, and germanium. This saw blade contains, that's A, contains carbon in the form of diamond. Silicon is used in the manufacture of microchips. Germanium is one of the materials used to make thermo-scanning goggles. So there are three uses. Okay, there's the saw, the diamond tip saw A, the microchip B, and the thermo scanning goggles, and that is going to be C. And there are many more uses for these elements. This is just three examples, so it's up to you to look up additional ones that you might find later on asked about on your test. Now, here are the groups. Now, you see how I have it labeled 1 through 1A through 8A, but I also have the corresponding 1, 2, 13, 14, 15, 16, 17, 18, and then the corresponding oxidation numbers. So that's a very, very important distinction when it comes to understanding the behavior of these. So those are the Lewis dot structures, they call them. Notice that all of the elements within a given group, with the exception of helium, have the same number of electron dots in their outer shell. So, but understand this, that don't think octet rule, think helium, inert, Y, 2 electrons, that's it, end of conversation. Same thing for all the other noble gases. Don't think 8, think let's match whatever that valence structure is. You learned in chapter 6 that noble gases such as neon and argon are unreactive in chemical reactions. That is, they are stable. In 1916, chemist Gilbert Lewis used this fact to explain why atoms form certain kinds of ions and molecules. He called his explanation the Octet Rule. In forming compounds, atoms tend to achieve the electron configuration of a noble gas in octet. An octet is a set of 8. Recall that each noble gas, except helium, has 8 electrons in its highest occupied energy level, and a general electron configuration of N, that's the shell, and S2, Np6. The octet rule takes its name from this fact about noble gases. The octet rule takes its name from this fact about noble gases, that most of the noble gases have 8 electrons in its valence shell, 8 octet rule. Atoms of metals tend to lose their valence electrons, leaving complete octet in the next lowest energy level. This is very important. Atoms of some nonmetals tend to gain electrons or to share electrons with another nonmetal to achieve a complete octet, with the exception of hydrogen, of course. Although there are exceptions, the octet rule applies to atoms in most compounds. An atom is electrically neutral because it has equal numbers of protons and electrons. An ion forms when an atom or group of atoms loses or gains electrons. An atom's loss of valence electrons produces a cation, or a positively charged ion. Note that for metals, the name of a cation is the same as the name of the element. For example, a sodium atom, Na, forms a sodium cation, Na+1. Likewise, a calcium atom, Ca, forms a calcium cation, Ca+2. Although their names are the same, there are many important chemical differences between metals and their cations. Sodium metal, for example, reacts explosively with water. By contrast, sodium cations are quite unreactive. As you may know, there are a component of table salt, a compound that is very stable in water. The most common cations are those produced by the loss of valence electrons from metal atoms. Most of these atoms have 1 to 3 valence electrons, which are easily removed. Sodium in group 1A, or just simply 1 of the periodic table, is typical. Sodium atoms have a total of 11 electrons, including one valence electron. A sodium atom can lose an electron to become a positively charged sodium ion. That entire group will become +1. The sodium ion has an electron configuration that is identical to the noble gas neon. When forming a compound, a sodium atom loses its one valence electron and is left with an octet, 8 electrons, in what is now its highest occupied energy level. Because the number of protons in the sodium nucleus is still 11, the loss of 1 unit of negative charge produces a cation with a charge of +1. Now, visually, this is what it looks like. You can represent the electron loss or ionization of the sodium atom by drawing the complete electron configuration of the atom and of the ion formed. So Na, there's the electron configuration, it ends in 3s1, loses that electron and forms, look at that, 2s2, 2p6, which is the same valence structure of neon, which is a noble gas. Notice that the electron configuration of sodium ion, 1s2, 2s2, 2p6, is the same as that of a neon atom. The diagrams below help illustrate this point. So there's the Aufbau rule and the filling of sodium. There's the giving up the electron. So that's the sodium ion. And then now let's compare it to the neon atom, which is inert, and it's the same. There is another look at it that's a little closer, a little blow-up look of it, and you can see that the loss of the valence electron produces that full 2p, that full 2p and 2s 8 electron valence that is very much the same as neon. Okay, so if you want to look at it, here we have both the sodium ion and the neon atom have 8 electrons in their valence shells, highest occupied energy level. Using electron dot structures, you can show the ionization more simply. So the Na with the dot, and you're losing the electron, and you're producing the Na +1 plus the electron. And then all the other information is in green. So let's look at the green information. It says sodium atom electrically neutral, the charge equals 0. Sodium ion, plus sign indicates 1 unit of positive charge, and then the electron minus sign indicates 1 unit of negative charge. So the loss of that valence electron will do two things. It will give the sodium atom the same valence as the neon atom, and it will also give it a +1 charge. Now, let's look at magnesium. Magnesium, atomic number 12, belongs to group 2A, or simply 2, of the periodic table. So it has 2 valence electrons. A magnesium atom attains the electron configuration of neon by losing both valence electrons. The loss of the valence electrons produces a magnesium cation with a charge of +2. So you see, just like the sodium, it's going to lose those 2 electrons in the Lewis dot structure. Magnesium atom electrically neutral, charge 0. Magnesium ion +2 indicates 2 units of positive charge, and then you have the 2 in front of the E indicates 2 units of negative charge. So the magnesium attains a charge of +2, and relative to bonding, so do all of the group 2 elements. They attain a charge of +2. Figure 2, the sodium atoms in a sodium vapor lamp ionize to form sodium cations, Na+1. Applying concepts, how many electrons are in the highest occupied energy level of Na plus? Well, it would be the same as neon. So it would have a full shell. How many would be 8, such as neon, and some additional material. What I did was I pulled some examples of this type of lighting. In London, England, for instance, there are few experiences more awe-inspiring than gazing into the night sky and seeing thousands of twinkling lights shining down on us, looking at the stars. Yet while the sight is amazing, the view from the other side, looking back down to Earth from outer space, is no less breathtaking. Stars, planets, and galaxies all seem to be echoed in these nightscape photographs of terrestrial cities taken from NASA's International Space Station, ISS. So I have some cities that are in focus, that are pictured in the slides, and you can see the presence of the sodium lamps, which are quite frequent around the city. That's London, England. So you can see the ring road going around London. You can see center London where the lights are brightest. And as you go out from the center, you have fewer lights, fewer bright lights. And so you can see the orange glow from the sodium vapor lamps. I'm sure there are other kinds of lighting as well, but that's the dominant one. That's a broader view. You can see some of the capitals of Europe there. You can see Paris and Brussels, London, Amsterdam. You see the English Channel, which is, you don't see any lighting. If you saw a cluster of ships, maybe the D-Day invasion armada, which probably had a blackout as well, so you might not have seen that either. The LPS lamp was the first sodium lamp to be developed. It is known by its signature monochromatic yellow color. It is mostly used in Europe since it did not appeal to other markets due to its poor CRI, or color rendering. It is among the most efficient lamps in the world because it uses all the current it gets to create light at the most sensitive color frequency to the human eye. An incandescent lamp, in contrast, creates light at all frequencies, from infrared, non-visible, to ultraviolet at the other end of the spectrum. The energy used to make non-visible light is a waste of energy since it does not help do the principal job of what? Of a lamp. So the incandescent light, matter of fact, 95% of the energy is wasted. It's only 5% efficient. It's better as an instrument for heating a room, the incandescent lamp, than it is for using it to light what you're seeing. Liège, Belgium. The city of Liège in Belgium creates some crazy, squiggly looking lines in this photograph. In fact, the pattern of the city looks almost organic, like magnified blood vessels. The photograph itself was shot with the European Space Agency's nodding mechanism. This relatively new piece of technology, also known as the night pod, was designed especially for space station usage and compensates for the station's movement relative to Earth, something that previously had to be done manually. As you can see, the results are impressive. And you would never guess that Liège, Belgium is surrounded by mountains and hills, very hilly place in the middle of the Ardennes forest. You would never know that that's a very, very hilly landscape. There seems to be mountains there seems to be lights all over the place. You can see the mountainous area. It almost looks like a topographical map in the outskirts, but Liège, Belgium is not on a plain. It's in the middle of a mountainous, not tall mountains, but mountainous area nonetheless, or very large hills, depending upon your point of view, I guess. Figure 3, walnuts are good dietary source of magnesium. magnesium ions, Mg+2, aid in the digestive process. They also help in the nerve conduction. You also need it for muscles and your nervous system. When you sweat profusely, you need to replace some of your electrolytes with various drinks, such as Gatorade. Here's a picture of some walnuts. Again, a great source of magnesium, and it helps with digestion. Magnesium, as I said, helps with other problems that could happen with your health if you're without magnesium. Formation of cations. Magnesium, atomic number 12, belongs to group 2A, or just 2, of the periodic table, so it has 2 valence electrons. A magnesium atom attains the electron configuration of neon by losing both valence electrons. The loss of the valence electrons produces a magnesium cation with a charge of +2. Figure 4 on the next page lists the symbols of cations formed by metals in group 1A and 2A. Cations of group 1A elements have a charge of 1, +1. Similarly, the cations of group 2A elements always have a charge of +2. Figure 4, cations of group 1A elements have a charge of +1. Cations of group 2A elements have a charge of +2. Group 1A is just 1, and 2A is just 2, depending upon which version of the periodic table you're using. So 1A is 1 and 2A is 2. So you're looking at the hydrogen is 1A, and then the beryllium is 2A. And there are the representative cations for those two groups, 1A and 2A, or simply 1 and 2. Okay, easy stuff. The consistency can be explained in terms of the loss of valence electrons by metal atoms. The atoms lose enough electrons to attain the electron configuration of a noble gas. For example, all group 2A elements have 2 valence electrons. In losing these 2 electrons, they form 2 cations. For transition metals, the charges of cations may vary. An atom of iron, for example, may lose 2 or 3 electrons. In the first case, it becomes iron +2 ion. And in the second case, although it's not listed here, it's iron +3. So red blood is iron +3. Dried blood is iron +2. In the second case, it forms iron +3 ion. Some ions formed by transition metals do not have noble gas configurations, as is listed there, and are therefore exceptions to the Octet Rule. Silver, with the electron configuration of, it ends in 4d10, 5s1, and that's really an off-bow filling particular reason, in a sense, I suppose you could argue that, is an example. So this really isn't an exception, it's an apparent exception. To achieve the structure of krypton, which is the preceding noble gas, a silver atom would have to lose 11 electrons. To acquire the electron configuration of xenon, which is the following noble gas, silver would have to gain 7 electrons. Ions with charges of 3 or greater are uncommon, and these possibilities are extremely unlikely. Thus, silver does not achieve a noble gas configuration, but if it loses its 5s1 electron, the configuration that results is 4s2, 5p6, 4d10, with 18 electrons in the highest occupied energy level and all of the orbitals filled is relatively favorable. Such a configuration is known as a pseudo-noble gas electron configuration. Silver forms a positive ion, Ag, in this way. Other elements that behave similarly to silver are found at the right of the transition metal block. Formation of cations still continued. For example, a copper atom can ionize to form a +1 cation, as is listed there, as illustrated. So that's what happens. That's the when you're talking about the off-bow filling, that's kind of has to do with that, where you're looking at energy differences to make something more energy efficient or lower energy, more energy stable. That's going to happen. By losing its lone 4s electron, copper attains a pseudo-noble gas configuration. Likewise, cations of gold, cadmium, and mercury also have pseudo-noble gas configurations. An anion is an atom or a group of atoms with a negative charge. The gain or negatively charged electrons by a neutral atom produces an anion. Note that the name of an anion of a non-metallic element is not the same as the element name. The name of an anion typically ends in IDE. We'll see that with nomenclature. That's very important. Thus, a chlorine atom, Cl, forms a chloride ion, Cl-1, and an oxygen atom forms an oxide ion, -2. Figure 5 on the next page shows the symbol of anions formed by some elements in groups 5a, 6a, and 7a. Figure 5, atoms of nonmetals and metalloids form anions by gaining enough valence electrons to attain the electron configuration of the nearest noble gas. Interpreting diagrams. In which group of the periodic table do the elements bromine and iodine belong? I hope you can get that. Okay, you've thought about it. It's the halogens, group 17 or 7a. There's 7a, the halogens, and there are the various representatives of the nonmetals, where arsenic and tellurium are considered metalloids by and large. They can be both metals or nonmetals, dependent because of their position in the periodic table. Because they have relatively full valence shells, atoms of non-metallic elements attain noble gas configurations more easily by attaining electrons than by losing them. For example, chlorine belongs to group 7a, the halogen family, and has 7 valence electrons. A gain of 1 electron gives chlorine an octet and converts a chlorine atom into a chlorine ion. And there's the configuration and the noble gas octet, which would be the same configuration. If I wrote out the electron configuration long form for argon, you'd get the same thing. So the chlorine will pick up 1 electron and be like argon. That's why it's doing it. It wants to be stable. It wants to have that configuration. The chloride ion is an anion with a single negative charge. Notice that it has the same electron configuration as the noble gas argon. And there is another indication with the brackets as to the octet, the 3s2 and 3p6. Remember, everything that bonds, usually, normally, let's not say everything, but has that octet business. Chlorine atoms, therefore, need 1 more valence electron to achieve an electron configuration of the nearest noble gas. The diagram below illustrates how both the chloride ion and the argon atom have an octet of electrons in their highest occupied energy levels. So That's important. And here we have the chlorine gaining an electron, and it becoming having that full P, so it'd be 3p6, and what else has 3p6? 3s2, 3p6, that's going to be argon. So it's going to look very, very similar to argon, which will make it very stable. Based on the diagrams above, you use electron dot structures to write an equation showing the formation of a chloride ion from a chlorine atom. In this equation, each dot in the electron dot structure represents an electron in the valence shell in the electron configuration diagram. Very important. Okay. The ions that are produced when atoms of chlorine and other halogens gain electrons are called halide ions. All halogen atoms have 7 valence electrons and need to gain only 1 electron to achieve the electron configuration of a noble gas. Thus, all halide ions have a charge of -1. The seawater in figure 6 on the next page contains many different ions, but the negatively charged ions, the anions, are mostly chloride ions. Look at another example. Oxygen is in group 6A, and oxygen atoms each have 6 valence electrons. Figure 6, the most abundant ions in seawater are chloride, that's a -1, the phosphate -2, sodium +1, magnesium +2, calcium +2, and potassium +1. And here is some seawater, some whales, some nice cyan-colored seawater, blue seawater, very nice. Some killer whales there. Here's a table with some ions, some important ions that you'll be using. The -1 ions, the fluoride, chlorine, chloride, bromide, iodide. There's some polyatomic ions, hydroxide, hypochlorite, the active ingredient in bleach, the -2, and then you have the -3 ions, nitride, and then the phosphide and phosphate. So very important ions. Formation of ions. Oxygen atoms attain the electron configuration of neon by gaining 2 electrons, as shown in the diagram on the next page. So that diagram will be similar to other diagrams that we've seen relative to the formation of the octet based on gaining or losing electrons. So in the case of an anion, you're going to be gaining electrons. So there you have the oxygen is going to gain 2 electrons, and then you have the -2 charge. So the oxygen atoms attain the electron configurations of neon by gaining 2 electrons, as shown in the diagrams below. The resulting oxide ions have charges of -2 and are written as O2. Using electron dot structures, you can write the equation for the formation of oxide ions as follows, and everything is right there. Very, very simple. Picture's worth 1,000 words. You have heard of harvesting crops such as wheat or rice, but salt? In many coastal countries that have warm, relatively dry climates, salt is produced by the evaporation of seawater. The salty water is channeled into a series of shallow ponds where it becomes more concentrated as the water evaporates. By exposing to the sun, when the seawater is concentrated enough, it is diverted into a pan on which the sodium chloride crystals deposit. Such farmers then drain the pans and collect the salt into piles to dry. In this section, you will learn how cations and anions combine to form stable compounds such as sodium chloride. And here are some examples of salt crystal formations in nature, be it on purpose or by accident. There's some harvesting salts. In the movie Gandhi, that was a major subplot, was the harvesting of the salts. Compounds composed of cations and anions are called ionic compounds. Ionic compounds are usually composed of metal cations and nonmetal anions. For example, sodium chloride or table salt is composed of sodium cations and chloride anions. Although they are composed of ions, ionic compounds are electrically neutral. The total positive charge of the cation equals the total negative charge of the anion. Ionic bonds. Anions and cations have opposite charges and attract one another by means of electrostatic forces. The electrostatic forces that hold ions together in ionic compounds are called ionic bonds. Sodium chloride provides a simple example of how ionic bonds are formed. Consider the reaction between a sodium atom and a chlorine atom. Sodium has a single valence electron that it can easily lose. If the sodium atom loses its valence electron, it achieves the stable electron configuration of neon. Chlorine has 7 valence electrons and can easily gain 1. You'll see on the next slide that the chlorine will achieve the valence configuration of argon. So they're both stable because of the configurations. If chlorine atom gains a valence electron, it achieves the stable electron configuration of argon. When sodium and chlorine react to form a compound, the sodium atom gives its 1 valence electron to a chlorine atom. On the next page, you're going to see a diagram that helps illustrate the bonding of sodium with chlorine. Here is the sodium giving its single electron from the 3s to chlorine, forming the octet. For sodium, it's going to be it'll be neon, or the second shell, and chlorine, it'll be argon, or the third shell. So that's the main idea, achieving the valence structure of the noble gases. Thus, sodium and chlorine atoms combine in a 1-to-1 ratio, and both ions have stable octets. Figure 7 on the next page shows aluminum and bromine reacting to form the compound aluminum bromide. Each aluminum atom has 3 valence electrons to lose. Each bromine atom has 7 valence electrons and readily gains 1 additional electron. Aluminum metal, figure 7, aluminum metal and the nonmetal bromine react to form an ionic solid, aluminum bromide. Okay, here's the aluminum metal in the form of a coin. Aluminum bromide is a white powder, and bromine is a liquid at room temperature that readily changes to a gas slightly above room temperature, depending on what you may consider to be room temperature. Therefore, when aluminum and bromine react, 3 bromine atoms combine with each aluminum atom. Formula units, the ionic compound sodium chloride is of equal numbers of sodium cations and chloride anions. As you see in figure 8 on the next page, the ions in solid sodium chloride are arranged in an orderly pattern. There are no single discrete units, only continuous array of ions. Chemists represent the composition of substances by writing chemical formulas such as NaCl, and that's a single formula unit is 1 particle of NaCl. Sodium cations and chloride anions form a repeating 3-dimensional array in sodium chloride, NaCl, a formula unit. Inferring, how does the arrangement of ions in a sodium chloride crystal help explain why the compound is so stable? So the next couple of pictures, you're going to see what the what the sodium chloride formula unit is composed of. And here you see that it's going to be made of sodium and chlorine, and what you're going to see is that this is not a unit cell, but this is a little bit bigger than a unit cell, but not much more. But you can see the how it forms its kind of cubic crystal, the way it's shaped. The positively and negatively charged ions in an ionic solid such as sodium chloride are held together by strong electrostatic interactions that form a neutral particle, and that particle is called a formula unit. The planes of the sodium chloride crystal reflect the regular three-dimensional arrangement of its Na plus, which is purple, and the Cl minus, which are green, those green ions. A chemical formula shows the kind and numbers of atoms in the smallest representative unit of a substance, such as sodium chloride, for example, is the chemical formula for sodium chloride. Note, however, that the formula NaCl does not represent a single discrete unit, because an ionic compound exists as a collection. It forms as a collection of positively and negatively charged ions arranged in repeating patterns. Its chemical formula refers to a ratio known as a formula unit. A formula unit is the lowest whole number ratio of ions in an ionic compound. For sodium chloride, the lowest whole number ratio of the ions in is 1:1, or 1 Na to 1 Cl. If its subscript is understood to be a 1, then it's 1. In other words, NaCl is no subscript, but the subscripts are inherent. They're understood to be 1, so they are indeed just 1. So it's 1 Na to each Cl. Thus, the formula unit for sodium chloride is NaCl. It's 1 Na and 1 Cl. Although ionic charges are used to derive the correct formula, they are not shown when you actually write the formula unit of the compound. The ionic compound magnesium chloride contains magnesium cations and chloride anions. In magnesium chloride, the ratio of magnesium cations to chloride anions is 1:2. 1 Mg plus 2 to 2 Cl minus 1, so its formula unit is MgCl2. Because there are twice as many chloride anions, each with a -1 charge, as magnesium cations, each with a +2 charge, the compound is electrically neutral. In aluminum bromide, described earlier, the ratio of aluminum cations to bromide anions is 1:3, 1 Al plus 3 to 3 Br minus 1 ions. So the formula unit is AlBr3. Remember, it's not called a molecule, it's a particle that is called a formula unit. Not a particularly pleasing term to name an individual particle. Molecule is much better. Figure 9 shows the striking beauty of crystals of some ionic compounds. Most ionic compounds are crystalline solids at room temperature. The component ions in such crystals are arranged in repeating three-dimensional patterns. The composition of a crystal of sodium chloride is typical. In solid NaCl, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. In this arrangement, each ion is attracted strongly to each of its neighbors and repulsions are minimized. The large attractive forces result in a very, very stable structure, such as salt mines, which are used to store nuclear material as long as they don't flood, or to house art collections or something like that. They're very stable, they remain environmentally very neutral, and much of that is due to the extremely stable structure of the ionic compound, such as sodium chloride. The beauty of crystalline solids such as these comes from the orderly arrangement of their component ions. So ionic compounds, because of their orderly arrangement, have very beautiful crystalline structures, such as these particular crystalline structures. You may be familiar with some of the names, or at least some of the common names for these rather technical terms, technical names, but they're very, very beautiful. This is reflected in the fact that sodium chloride has a melting point of about 800 degrees Celsius. Ionic compounds generally have high melting points. The coordination number of an ion in the number of ions of opposite charge that surround the ion is a crystal. Figure 10a shows the three-dimensional arrangement of ions in sodium chloride. Because each Na ion is surrounded by 6 Cl-1 ions, Na has a coordination number of 6. Each Cl-1 ion is surrounded by 6 Na ions and also has a coordination number of 6. Cesium chloride, CsCl, has a coordination number similar to that of sodium chloride. Figure 10, sodium chloride and cesium chloride form cubic crystals. A. In sodium chloride, each ion has a coordination number of 6. In B, cesium chloride, each ion has a coordination number of 8. Titanium dioxide forms tetragonal crystals. In Ti, titanium oxide, TiO2, each titanium ion has a coordination number of 6, while each O, oxygen plus 2 ion, has a coordination number of 3. So these coordination numbers are very, very important, and we will talk about them in further chapters. However, A is sodium chloride with a coordination number of 6, cesium chloride has a coordination number of 8, and so on. So here is sodium chloride is A, the chlorine is green and the sodium is yellow, etc. And cesium chloride is B, and titanium oxide is C. As figure 10b on the next page illustrates, both compounds have cubic crystals, but their internal crystal structures are different. Each cesium ion is surrounded by 8 chloride ions, and each chloride ion is surrounded by 8 cesium ions. The anion and cation in cesium chloride each have a coordination number of 8. Figure 10c on the next page shows the crystalline structure of titanium, TiO2, also known as rutile. In this compound, the coordination number for the cation, titanium plus 4, is 6. Each titanium plus 4 ion is surrounded by 6 O negative 2 ions. The coordination number of the anion, O negative 2, is 3. So here's the picture of B and C as seen before. The cesium chloride, cesium has a coordination number of 8, as you can see by the picture, and the 8 chloride ions. And rutile, or TiO2, titanium oxide, you can see that it has a coordination number of, the titanium has a coordination number of 6 and oxygen 3. Each O2 ion is surrounded by 3 titanium 4 ions. Another characteristic property of ionic compounds has to do with conductivity. Ionic compounds can conduct an electric current when melted or dissolved. That's so the particle can go from place to place within the liquid. As figure 11 on the next page shows, when sodium chloride is melted, the orderly crystalline structure breaks down. If a voltage is applied across this molten mass, cations migrate freely to one electrode and ions migrate to the other. This Ion movement, this migration, which is only allowed in the liquid state, allows electricity to flow between the electrodes through an external wire. Figure 11, when sodium chloride melts, the sodium and chloride ions are free to move throughout the molten salt. If a voltage is applied, positive sodium ions move to the negative electrode, the cathode, and negative chloride ions move to the positive electrode, the anode, predicting what would happen if the voltage was applied across a solution of sodium chloride dissolved in water. So the same thing would happen as long as because they're charged particles, as long as they're able to migrate. They're not able to migrate in the crystalline solid form. They're only able to migrate if they're melted or if they're in water. Now you're going to say to yourself, well, water can conduct electricity. No, water cannot conduct electricity. The material that's dissolved in water is actually conducting the electricity, such as sodium chloride. So here is an example of sodium chloride. This could be molten sodium chloride, or it could be sodium chloride dissolved in water. In this case, it's molten. You see the L for liquid in parentheses next to the chloride ion and the sodium ion, and it's molten. So the chlorine becomes a gas, and the sodium, they're saying, becomes a liquid because it's warm. Otherwise, it would be a solid. A down cell for the electrolysis of molten sodium chloride or molten calcium chloride. The electrolysis of a molten mixture of sodium chloride and calcium chloride results in the formation of elemental sodium and chlorine gas. Because sodium is a liquid under these conditions and liquid sodium is less dense than molten sodium chloride, here you can see the molten material. On the right, it says molten sodium chloride, calcium chloride, and it's pointing to that. There's where, on the top is where you put it all in. I think, where was I? Because sodium is a liquid under these conditions, and liquid sodium is less dense than molten sodium chloride, the sodium floats to the top of the melt and is collected in concentric capped iron surrounding the cathode. I'll show you that in a moment. Let's actually look at that right now and see what that looks like. You can see the iron screens. That's the actual anode. That whole setup that runs behind is the anode, and the graphite platform is actually the anode. Okay, gaseous chlorine collects in an inverted cone over the anode. An iron screen separating the cathode and anode compartments ensures that the molten sodium and gaseous chlorine do not come into contact. That's something that's also very important. Let me stop this tape and let's look at that structure again for a moment. So here is the apparatus again. You see the black platform in the middle, lower middle, and that is going to be the anode. That's where the anode, which is positive, attracts the chlorine when it's in the liquid state, the chlorine ion, and then it's turned to gas, and it goes out to chute. You see Cl2 outlet. You see the iron screen that separates the chlorine gas from the sodium melt that floats and is taken out on the left where sodium liquid is taken out. Okay, so here's for a similar reason, ionic compounds also conduct electricity if they are dissolved in water, as we've discussed. When dissolved, the ions are free to move about in the aqueous solution, as long as they're allowed to migrate. That's why you can't have them in a solid, not in a solid state, the crystalline form, because the particles are locked and they can't actually migrate. So as long as they're in the molten or solution form, they will conduct electricity. It's actually, water does not conduct electricity. It's the material that's dissolved in water that conducts electricity. Water is a non-electrolyte material. It does not conduct electricity. You have probably seen decorative fences, railings, or weather vanes made of a metal called wrought iron. Wrought iron is a very pure form of iron that contains trace amounts of carbon. It is a tough, malleable, ductile, and corrosive resistant material that melts at a very high temperature. As you already know, metals often have distinctive, useful properties. In this section, you will learn how metallic properties derive from the way that metal ions form bonds with one another. I once had to scrape, prime, buff, and then paint again this rather large fence around a university. All summer it took me. It was a monstrous job. I had to wear masks, and God, it was awful. It was, when I see fences like that, I think of one thing, and that is working really hard. It was an amazing job. But that's wrought fencing, and as you can see, it's very useful. So we're going to be looking at essentially transition metals and how useful they are because of their bonding structure. Metals are made up of closely packed cations rather than neutral atoms. The valence electrons of metal atoms can be modeled as a sea of electrons. That is, the valence electrons are mobile and can drift freely from one part of the metal to another. Metallic bonds consist of the attraction of the free floating valence electrons for the positively charged metal ions. These bonds are the forces of attraction that hold metals together. The sea of electrons model explains many physical properties of metals. For example, metals are good conductors of electrical current because electrons can flow freely in them. As electrons enter one end of a bar of metal, an equal number of electrons leave the other end. Metals are ductile, that is, they can be drawn into wire, as shown in figure 12 on the next slide. Metals are also malleable, which means they can be hammered or forced into shapes. Both the ductile and malleability of metals can be explained in terms of the mobility of valence electrons. A sea of drifting valence electrons insulates the metal cations from one another. So the ductility and malleability of metals can be explained in terms of the mobility of valence electrons. Rather a significant sentence. A metal rod can be forced through a narrow opening in a die to produce wire. It's called ductility. As this occurs, the metal changes shape but remains in one piece. That's going to be A on the next slide. If an ionic crystal were forced through a die, it would shatter. What causes the ionic crystal to shatter? It's the fact that it's a crystal. It has a definite shape, definite solid shape, designed solid shape. So there is the ductility of the transition element, and with metallic bonds. And A, you see this sea of electrons and the metal cations and etc. And it can be squeezed through the die, whereas the ionic solid crumbles. When a metal is subject to pressure, the metal cations easily slide past one another like ball bearings immersed in oil. In contrast, if an ionic crystal is struck with a hammer, the blow tends to push the positive ions close together. They repel, and the crystal shatters. So interestingly enough, even the shattering has to do with electricity, so to speak. The next time you visit a grocery store, take a look at how the apples or tomatoes are stacked. More than likely, they will have a close packed arrangement as shown in figure 13 on the next slide. This arrangement helps save space while allowing as many tomatoes to be stacked as possible. Similar arrangements can be found in the crystalline structures of metals. You may be surprised to learn that metals are crystalline. In fact, metals that contain just one kind of atom are among the simplest forms of all crystalline solids. When you think of a crystal, you think of something like a diamond or diamond shape or some kind of precious mineral that has a unique, beautiful shape. People don't think of a metal as having that same kind of crystalline structure. Figure 13, these tomatoes illustrate a pattern called hexagonal close-packed arrangement. Many things in nature have this hexagonal close-packed arrangement. It is an efficient way of storing matter, of storing material. Compounds use it, snowflakes use it, things that are stacked on a shelf in a grocery store use it. It's used in beehives. You'll see it. You'll see you'll see it in insect eyes. Kind of weird looking, isn't it? A little scary. Looks like something out of a sci-fi picture. You have on Saturn's northern hexagon. It's amazing how they could even get that picture. I doubt it's the Hubble telescope, could be, or one of the deep space crafts, deep space exploratory crafts like Pioneer or Voyager. And then there's the snowflakes, which are amazing in and by themselves. They're all quite different, yet they have this hexagonal shape to them. Metal atoms are arranged in very compact and orderly patterns. For spheres of identical size, such as metal atoms, there are several closely packed arrangements that are possible. Figure 14 on the next page shows three such arrangements: body-centered cubic, face-centered cubic, and hexagonal close-packed arrangements. In a body-centered cubic structure, every atom, except those on the surface, has 8 neighbors. The elements sodium, potassium, iron, chromium, and tungsten crystallize in a body-centered cubic pattern. In a face-centered cubic arrangements, every atom has 12 neighbors. Figure 14, metal atoms crystallize in characteristic patterns. A, chromium atoms have a body-centered cubic arrangement. Gold atoms have a face-centered cubic arrangements, and zinc atoms have a hexagonal close-packed arrangement, inferring which of these arrangements is the most closely packed. So here are the three arrangements. Chromium A on the left, body-centered cubic, and then gold on the in the middle, and that is going to be face-centered cubic, and then the zinc, which is hexagonal close-packed, and that is going to be on the right, that's C. So the answer to the question, the inferring, is obviously the close-packed, the zinc. Figure 15, bicycle frames are often made of titanium alloys that contain aluminum and vanadium. So titanium can also include aluminum and vanadium. Each of these metals contributes to the alloy in specific ways. The study of alloys, metallurgy, is a very complicated field and a very fascinating one. Here's the bicycle. Here's a bicycle that's composed of a titanium alloy, again, which contains aluminum and vanadium. Where is vanadium and what is its symbol on the periodic table? Where is vanadium on the periodic table? What is its atomic number? First one to tell me in class after the bell will get extra credit. Among the metals that form a face-centered cubic lattice are copper, silver, gold, aluminum, and lead. In a hexagonal close-packed arrangement, every atom also has 12 neighbors. Because of its hexagonal shape, however, the pattern is different from the face-centered cubic arrangements. Metals that have the hexagonal close-packed crystal structure include magnesium, zinc, and cadmium. They have the hexagonal close-packed crystalline structure. Alloys. Although every day you use metallic items such as spoons, very few of these objects are pure metals. Instead, most of the metals you encounter are alloys. Alloys are mixtures composed of two or more elements, at least one of which is a metal. Brass, for example, is an alloy of copper and zinc. Alloys are important because their properties are often superior to those of their component elements. Sterling silver, 92.5% silver, and 7.5% copper, is harder and more durable than silver, pure silver, but still soft enough to be made into jewelry and tableware. Table 3 lists the composition of some common alloys. Alloys can form from their component atoms in different ways. If the atoms of the components in an alloy are about the same size, they can replace each other in the crystal. This type of alloy is called a substitutional alloy. If the atomic sizes are quite different, the smaller atoms can fit into the interstices, the interstitial spaces between the larger atoms. Such an alloy is called an interstitial alloy. In the various types of steel, for example, carbon atoms occupy the spaces between the iron atoms. Thus, steels are interstitial alloys. Modern architecture would be a lot shorter if it weren't for steel. Since the late 1800s, using steel columns and girders in construction has allowed architects to design taller, stronger, and lighter buildings. Unlike buildings made of wood, brick, or stone, steel structures are strong enough to accommodate large, open interior spaces that do not require supporting walls. Usually, you can't see the steel used to construct a building. Either it's hidden by the floors and walls, or in the case of a building made of reinforced concrete, it's actually embedded in the floors and the walls, or the columns that are made of the concrete. It's hidden by the concrete. The exteriors of buildings often feature lighter alloys, such as alloys of aluminum or titanium that resist corrosion. Comparing and contrasting, how does steel frame construction differ from reinforced concrete construction? Here is Table 3, which I mentioned 3 slides earlier. It's the composition of some common alloys. Sterling silver, predominantly silver with some copper. Cast iron, iron with a little carbon. Stainless steel, you've heard of that, sinks and things that you don't want to rust, severely anyway, has chromium, carbon, and nickel in it. Spring steel. Surgical steel, very precious stuff, very expensive. Look at that. It has a lot of nickel in it and some molybdenum. So that makes it very special, doesn't rust, keeps its shape. So those are simply 5 alloys, but there are many, many, many alloys. Oftentimes, again, the alloys are far better than any of the metals that they are made of. So we will learn more about alloys. Alloys are actually a solution. You know, you're familiar with solutions when you say water and sugar or water and salt. That's a solution. Well, an alloy is also a solution. It's a solid, solid, solid solution, depending upon how many solids are in there. So we'll study alloys more thoroughly as the year goes on. These toys are made from circular pieces joined together in units by sticks. Although the types of pieces are limited, there can be many different models depending on how many pieces are used and how they are arranged. As with the circular pieces, there are a limited number of different types of atoms, but atoms can also be arranged in different ways to make up a variety of products. In this section, you will learn how atoms can share electrons to form a bond called a covalent bond, and how the atoms join to form units called molecules. So now we just finished ionic bonding, and now we're going to start covalent bonding. Here is a set of Tinker Toys, and you could think of Tinker Toys as atoms and bonds. The straws or the tubes are bonds, and then you have the central atom that goes to atoms that are covalently bound to the central atom. So we will do a lab similar to this, but with clay and toothpicks. But Tinker Toys can hold the key to many of the covalent molecules that we will study. In nature, matter takes many forms. The noble gas elements, such as helium and neon, shown in Figure 1 on the next page, exist as atoms. They are monatomic, that is, they consist of single atoms. You learned in the previous chapter that atoms of some elements combine to form ionic compounds. These compounds are crystalline solids with high melting points. Other compounds, however, can have very different properties. Hydrogen chloride, for example, is a gas at room temperature. Water, H2O, is a liquid at room temperature. The noble gases, including helium and neon, are monatomic. That means they exist as single atoms. Helium, being less dense than air, is often used to inflate balloons. The colors produced in what we commonly call neon lights are a result of passing an electric current through one or more noble gases. When we think of noble gases, we often think of neon, which is in the lower right or the lower left. Helium, I'm not sure it's going to move a house, but fair enough. Argon is often used in science, in experimentation, to help create a vacuum. Krypton, radon is often found in basements of houses. You oftentimes have to get certification that you don't have a lot of radon in your basement, so it's tested by law. And unlike helium, it's much heavier than air and will fall in air, and it will end up in the basement. That's why basements have to be tested. It will seek the lowest level in the house, in the structure. These two compounds are so different from ionic compounds that you might correctly suspect that attractions between ions fail to explain their bonding. Such compounds are not ionic. Their combining atoms do not give up electrons or accept electrons. Instead, a tug of war for electrons takes place between the atoms, bonding the atoms together. The atoms held together by sharing electrons are joined by a covalent bond. Some elements found in nature are in the form of molecules. A molecule is a neutral group of atoms joined together by covalent bonds. For example, air contains oxygen molecules as well as nitrogen molecules, O2, N2. You can also have hydrogen forms a diatomic molecule. Each oxygen molecule consists of two oxygen atoms joined by covalent bonds. A diatomic molecule is a molecule consisting of two atoms. An oxygen molecule is a diatomic molecule. Atoms of different elements can combine chemically to form compounds. In many compounds, atoms are bonded to each other to form molecules. Examples include water and carbon monoxide, which are described in Figure 2 on the next page. A compound composed of molecules is called a molecular compound. The molecules of a given molecular compound are all the same. So is an ionic compound are made of individual formula units that are all the same. Many of the nonmetals will form covalent bonds. Figure 2, water is a molecular compound with molecules composed of 2 hydrogen atoms and 1 oxygen atom. Carbon monoxide is a molecular compound with molecules composed of 1 carbon atom and 1 oxygen atom. Carbon monoxide will compete with oxygen to adhere to the hemoglobin and can cause asphyxiation if there's too much carbon monoxide in a particular area. So carbon monoxide can be very dangerous. Here is carbon monoxide with a triple bond. Here we have water with the single bonds. And you can see how the little partial negative charge on the oxygen on one molecule can combine with the little partial positive charge on the other and form these physical bonds. We have single bonds there, approximately 109.5 degrees, approximately. Remember, there is no such thing as a molecule of sodium chloride or magnesium chloride. Instead, these ionic compounds exist as collections of positively and negatively charged ions arranged in repeating three-dimensional patterns. Recall from Chapter 7 that the composition of ionic compounds is expressed as formula units. Molecular compounds tend to have relatively lower melting and boiling points than ionic compounds. Many molecular compounds are gases or liquids at room temperature. Many of the ionic compounds, salts, are solid at room temperature. Carbon dioxide, carbon monoxide, sulfur dioxide, hydrogen disulfide, these are all gases at room temperature. In contrast to ionic compounds, which are formed from metal combined with nonmetal, most molecular compounds are composed of atoms of 2 or more nonmetals. For example, 1 atom of carbon can combine with 1 atom of oxygen to form 1 molecule of a compound known as carbon monoxide. Carbon monoxide is a poisonous gas produced by burning gasoline in internal combustion engines. Figure 3 on the next page illustrates some differences between ionic and molecular compounds using sodium chloride and water as examples. Sodium chloride, which is an ionic compound, and water, which is a molecular compound, are compared here, interpreting diagrams. How do molecular compounds differ from ionic compounds, such as what I mentioned on the next page? You should take some notes which will help you distinguish between ionic and covalent compounds relative to their properties for your test on bonding. Now, here are examples of sodium chloride and water and why they're a little different, etc. Here you have sodium chloride. It looked like the Bohr model of the atom there, and you have here you have this nice collection of positive and negative charges. Here I have the sodium is giving up an electron to chlorine, and you're creating these 2 separate entities. Here we have salt mining, and it's a pretty amazing structure. That's some kind of tractor at the top there. Here we have water. We have 104.4, which is close to 109.5. That's actually the tetrahedral. So and we'll look at that in more in depth in bonding. You have the van der Waals radius. We're going to look at that more in later chapters. The hydrogen bonding, and here we have dipole water vapor, electrical structure, etc. So that's going to come in very important in later chapters. A molecular formula is the chemical formula of a molecular compound. A molecular formula shows how many atoms of each element or molecule contains. A molecular formula shows how many atoms of each element a molecule contains. A water molecule consists of 2 hydrogen atoms and 1 oxygen atom. The molecular formula of water is H2O. Notice that a subscript written after the symbol indicates the number of atoms of each element in the molecule. If there is only 1 atom, the subscript 1 is omitted. The molecular compound for carbon dioxide is CO2. This formula represents a molecule containing 1 carbon atom and 2 oxygen atoms. As shown in figure 4 on the next page, ethane, a component of natural gas, it's part of the alkanes. Octane is part of the alkanes as well, is also a molecular compound. The molecular formula for ethane is C2H6. According to this formula, 1 molecule of ethane contains 2 carbon atoms and 6 hydrogen atoms. A molecular formula reflects the actual number of atoms in each molecule. The subscripts are not necessarily lowest whole number ratios. Molecular formulas also describe molecules consisting of 1 element. Because the oxygen molecule consists of 2 oxygen atoms bonded together, its molecular formula is O2, such as H2, 2 atoms of hydrogen. Ethane is a component of natural gas, inferring what information about the ethane molecule given by its molecular formula C2H6 is also given by the drawing shown here. Ethane can be expressed in structural formulas. It shows which atoms are bonded together, and then you see the flame, the blue flame, which is characteristic of natural gas. On the next slide, we'll talk about different ways of expressing formulas. A molecular formula does not tell you about a molecule's structure. In other words, it does not show either the arrangement of the various atoms in space or which atoms are covalently bonded to one another. A variety of diagrams and molecular models, some of them illustrated in figure 5 on the next page, can be used to show the arrangement of atoms in a molecule. Diagrams and models like these will be used throughout the textbook. Figure 6 shows the chemical formulas and structures of some other molecular compounds. Ammonia, NH3, is used in solution as a cleaning agent. You can represent the ammonia molecule by its molecular formula, its structural drawing formula, a space-filled molecular model, a perspective drawing, space-filling molecular model, or a ball and stick molecular model. Ammonium is a polyatomic ion closely associated with ammonia. Ammonium is produced when you mix ammonia with water. You produce ammonium hydroxide. Ammonium is a polyatomic ion, NH4 with a positive 1 charge. It combines with hydroxide, OH negative 1, and you get that from water. Here are the various types of structure. You have 107 degrees between the hydrogens that are kind of out of the plane and below the central molecule. So here are the different perspectives going clockwise, and that is ammonia and ammonium. You see that the ammonium has the positive 1 charge. Carbon dioxide, for example, is a gas produced by the complete burning of carbon. It is found in Earth's atmosphere and dissolved in seawater. It is also used to carbonate beverages. The molecular structure of carbon dioxide in figure 6 on the next page shows how the carbon atom in each molecule has two oxygen atoms on opposite sides of it. It shows how the three atoms are arranged in a row. It's called linear. That's the geometry of it. The molecular structure of water shows how the hydrogen atoms, in contrast, are mainly on one side of the water molecule. The water molecule, that is called a bent geometry. Figure 6, the formula of a molecular compound, indicates the numbers and kinds of atoms. The arrangement of the atoms within a molecule is called its molecular structure. Using models, which of these molecules has the greatest number of oxygen atoms? You can simply count on the structure to tell. Here are the three molecules: water, carbon dioxide, and ethanol. The counts are there. It's very obvious to see. You can even see the geometry that exists among the atoms that form the individual molecules. The molecular structure of ethanol is more complicated, but the molecular structure illustrated in Figure 6 also shows how many of each kind of atom are in each molecule and how the atoms are arranged with respect to one another. You know that without oxygen to breathe, you could not live. But did you know that oxygen plays another important role in your life? High in the atmosphere, a different form of oxygen called ozone forms a layer that filters out harmful radiation from the sun. The colors in this map indicate the concentration of ozone in various parts of Earth's atmosphere. In this section, you will learn how oxygen atoms can join in pairs to form the oxygen you breathe, and can also join in groups of 3 oxygen atoms to form ozone. Here are the different patterns of ozone measured photographically in different years in the Earth's atmosphere, taken from space in some fashion. Recall that when ionic compounds form, electrons tend to be transferred so that each ion acquires a noble gas configuration. A similar rule applies for covalent bonds. In covalent bonds, electron sharing usually occurs so that atoms attain the electron configuration of noble gases. For example, each hydrogen atom has 1 electron, but a pair of hydrogen atoms share these 2 electrons when they form a covalent bond in a hydrogen molecule. Each hydrogen atom thus attains the electron configuration of helium, a noble gas with 2 electrons. Again, the octet rule is just referring to the noble gas configuration. Combinations of atoms of nonmetals and metalloids in groups 4A, 5A, 6A, and 7A of the periodic table are likely to form covalent bonds. In this case, the atoms usually acquire a total of 8 electrons, or an octet, by sharing electrons, so that the octet rule applies. Look at the regular numbering of that table for those various columns. For instance, 4 is going to be 14, so it'll be 14, 15, 16, 17. That'll be 4A, 5A, 6A, 7A. So make sure you make those, you know what columns they're talking about when the book says 4A, 5A, 6A, and 7A. The hydrogen atoms in a hydrogen molecule are held together mainly by the attraction of the shared electrons to the positive nuclei. 2 atoms held together by sharing a pair of electrons are joined by a single covalent bond. Hydrogen gas consists of diatomic molecules whose atoms share only 1 pair of electrons, forming a single covalent bond. Here is hydrogen, and here is the bonding structure. Look at the two fillings of hydrogen in the 1s. You're just simply combining the two and in opposite spins, and you're creating a single covalent bond as a result. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, they all form this diatomic structure where they're sharing that one electron. Here's another shot at it. Each hydrogen has a noble gas configuration. An electron dot structure, such as H dot dot H, represents the shared pair of electrons of a covalent bond by two dots. The pair of shared electrons forming the covalent bond is also often represented as a dash, as in H dash H for hydrogen. A structural formula represents the covalent bonds by dashes and shows the arrangement of covalently bonded atoms. In contrast, the molecular formula of hydrogen, H2, indicates only the number of hydrogen atoms in each molecule. The halogens also form single covalent bonds in their diatomic molecules. Fluorine is one example. Because a fluorine atom has 7 valence electrons, it needs one more to attain the electron configuration of a noble gas. By sharing electrons and forming a single covalent bond, 2 fluorine atoms each achieve the electron configuration of neon. So we're going to see a couple slides of that. Here's 2 fluorine atoms. Here's the filling, 1s2, 2s2, 2p5, and here's how it's done. And you form F2, to form a fluorine molecule, and you're forming this octet by the sharing of the electrons. So fluorine does it quite easily. They just simply share one electron. Share one, you get one. So this is fluorine, and very simply done. And just think, when you're thinking of fluorine, think each fluorine has a noble gas configuration, octet, such as neon. In the F2 molecule, each fluorine atom contributes 1 electron to complete the octet. Notice that the 2 fluorine atoms share only one pair of valence electrons. A pair of valence electrons that is not shared between atoms is called an unshared pair, also known as a lone pair or a non-bonding pair. You can draw electron dot structures for molecules of compounds in much the same way that you draw them for molecules of diatomic elements. Water, H2O, is a molecule containing 3 atoms with 2 single covalent bonds. 2 hydrogen atoms share electrons with 1 oxygen atom. So water is going to be a dominant structure in this book. Here we have the bonding of the covalent bonding of the hydrogen with the oxygen, and it's clearly covalent, and you're sharing, the water is sharing electrons in terms of the oxygen shares 1 electrons with the hydrogen, so you get that covalent bond, and it does it with the other hydrogen. So you get two covalent bonds in the water molecule by the sharing. The hydrogen gives up 1 to share, the oxygen gives up 1 to share. You give 1 to share, you get 1. So you give 1 to share, you get 2. So hydrogen has the helium valence structure, and oxygen has the neon valence structure. Here is the reaction that produces ammonia. So you have this way of representing it with Lewis dot structures, with a line being a pair of electrons, and then you have the filling, and the opposite pair in the lower left opposing one another, and they simply slide in together. And then we have methane, which is a tetrahedral molecule. Each hydrogen and the carbon has a noble gas configuration, an octet, helium for the hydrogen and neon for the carbon. So you have water, ammonia, and methane, all covalent, and gases at room temperature as well. So very different from ionic compounds. The hydrogen and oxygen atoms attain noble gas configurations by sharing electrons, as we've just seen. As you can see in the electron dot structures below, the oxygen atom in water has two unshared pairs of valence electrons. You can draw the electron dot structure for ammonia and H3, a suffocating gas, in a similar way. The ammonia molecule has one unshared pair of electrons. Methane, CH4, contains 4 single covalent bonds. The carbon atom has 4 valence electrons and needs 4 more valence electrons to attain a noble gas configuration. With any kind of bonding, you have to always consider what is the corresponding noble gas configuration that is sought by each atom involved in a molecule, or an ionic compound for that matter. Each of the 4 hydrogen atoms contributes 1 electron to share with the carbon atom, forming 4 identical carbon-hydrogen bonds. As you can see in the electron dot structure below, methane has no unshared pairs of electrons. When carbon forms bonds with other atoms, it usually forms 4 bonds. You would not predict this based on carbon's electron configuration shown below. So you're going to have what we're going to call a hybrid molecule, where you have that 2s2 electron, the one that's in the down position on the right of the first orbital of that s orbital, is going to go into the third orbital for the 2p. If you tried to form covalent CH bonds for methane by combining the 2p electrons of the carbon with 2 1s electrons of a hydrogen atom, you would incorrectly predict a molecule with a formula of CH2 instead of CH4. So you're going to have this hybridization. It's called sp3. The formation of 4 bonds by carbon can be simply explained. One of carbon's 2s electrons is promoted to the vacant 2p orbital to form the following electron configuration. This electron promotion requires only a small amount of energy. The promotion provides 4 electrons of carbon that are capable of forming covalent bonds with 4 hydrogen atoms. That was in the former slide. Methane, the carbon compound formed by electron sharing of carbon with 4 hydrogen atoms, is much more stable than CH2. The stability of the resulting methane more than compensates for the small energy cost of the electron promotion. Therefore, formation of methane, CH4, is more energetically favored than the formation of CH2. Sometimes atoms bond by sharing more than 1 pair of electrons. Atoms form double or triple covalent bonds if they can attain a noble gas configuration by sharing 2 pairs or 3 pairs of electrons. A bond that involves 2 shared pairs of electrons is a double covalent bond. A bond formed by sharing 3 pairs of electrons is a triple covalent bond. You might think that an oxygen atom with 6 valence electrons would form a double bond by sharing 2 of its electrons with another oxygen atom, and that's going to be to form an O2 molecule, and that's exactly what happens. It's O double bond O, and here that is illustrated in the next slide, where you have a double bond. So, and you can see how oxygen is pairing up in the lower left-hand corner with the off-bow filling of those various orbitals, and how they combine to form the double bond. Each oxygen has a noble gas configuration, or an octet of neon. So there is the representation of those various structures for oxygen. And here's nitrogen, where nitrogen is forming a triple bond, and there is the filling of the nitrogen. It just so happens that nitrogen is perfect. It's a 1s2, 2s2, 2p3. So each orbital has one electron, and you can easily pair that with another one. So nitrogen will form a triple bond quite readily with another nitrogen. So that's why N2 is extremely stable. Here's another example of nitrogen, 3 bonds, N2, and oxygen has double bonds, O2. And if you simply count the electrons, you'll see that each atom, N, and O, are stable because they all achieve the octet of neon. And so you can see why nitrogen is also very stable, again, because of the triple bond. In such an arrangement, all electrons within a molecule would be paired. Experimental evidence, however, indicates that 2 of the electrons in O2 are still unpaired. Thus, the bonding in the oxygen molecule does not obey the octet rule. You can draw an electron dot structure that inadequately describes the bonding in the oxygen molecule. An element whose molecules contain triple bonds is nitrogen, N2, a major component of the Earth's atmosphere, illustrated in Figure 7 on the next page. In the nitrogen molecule, each nitrogen atom has one unshared pair of electrons. Oxygen and nitrogen are the main components of Earth's atmosphere. The oxygen molecule is an exception to the octet rule. It has 2 unpaired electrons. 3 pairs of electrons are shared in a nitrogen molecule. And the next slide, it just shows you simply various aspects of oxygen, and it just shows you pictures of the Earth and its beautiful atmosphere. And it's all made of nitrogen and oxygen. And the snow is made of oxygen as well, and hydrogen in terms of water, frozen water. But the picture is just simply to show you the beautiful atmosphere, the blue and the high degree of nitrogen and oxygen in the atmosphere. And that's what it's there. That's why the figure is there, and for no other reason. A single nitrogen atom has 5 valence electrons. Each nitrogen atom in the nitrogen molecule must gain 3 electrons to have the electron configuration of neon. Up to this point in your textbook, the examples of single and triple covalent bonds have involved diatomic molecules such as N2 and O2. Those are double and triple bonds, or triple and double bonds. The nitrogen is N2, that's triple, and the O2 is double bond. Table 1, approximately on the next page, lists the properties and uses of elements that exist as diatomic molecules. Single, double, and triple covalent bonds can also exist between unlike atoms. For example, consider carbon dioxide, which is present in the atmosphere and used to carbonate many soft drinks, as shown in Figure 8, approximately on the next page. Here is Table 1, and it shows the diatomic molecules and their bonding structure from single to triple bond. And carbon dioxide gas is soluble in water and is used to carbonate many beverages. A carbon dioxide molecule has 2 carbon-oxygen double bonds. And here is an example of how the carbonation is coming out of the soda and forming fizzing. It's fizzing. It's actually bringing the liquid out with it. in an explosion of effervescence. Here is the carbon dioxide molecule, how you have the two double bonds. There in the lower left-hand corner, you have the order of filling and how the unpaired single electrons are combining to form bonds, and each carbon and oxygen has a noble gas configuration or an octet, such as for neon. The carbon dioxide molecule contains two oxygens, each of which shares two electrons with carbon to form a total of two carbon-oxygen double bonds. The two double bonds in the carbon dioxide molecule are identical to each other. Carbon dioxide is an example of a triatomic molecule, which is a molecule consisting of three atoms. Carbon monoxide, CO, is an example of a type of covalent bonding different from that seen in water, ammonia, methane, and carbon dioxide. A carbon atom needs to gain 4 electrons to attain the electron configuration of neon. An oxygen atom needs 2 electrons. Yet it is possible for both atoms to achieve noble gas electron configuration by a type of bonding called coordinate covalent bonding. To see how, begin by looking at the double covalent bond between carbon and oxygen. With the double bond in place, the oxygen has a stable configuration, but the carbon does not. And what is going to happen is, as you'll see in the next slide, the coordinate covalent bond comes from the electrons entirely from oxygen. You have a normal sharing, as we know, in bonding, in covalent bonding, where you have the two red bonds are typical covalent bonds, but the green bond is completely from the oxygen atoms, those two electrons, and it forms a bond, and so everything is satisfied. As shown below, as I just showed you, the dilemma is solved if the oxygen also donates one of its unshared pairs of electrons for bonding. A coordinate covalent bond is a covalent bond in which one atom contributes both bonding electrons. In a structural formula, you can show coordinate covalent bonds as arrows that point from the atom donating the pair of electrons to the atom receiving them. The structural formula of carbon monoxide with 2 covalent bonds and 1 coordinate covalent bond is C triple bond O. In a coordinate covalent bond, the shared electron pair comes from one of the bonding atoms. Once formed, a coordinate covalent bond is like any other covalent bond. The ammonium ion consists of atoms joined by covalent bonds, including a coordinate covalent bond. A polyatomic ion, such as NH4 plus 1, is a tightly bound group of atoms that has a positive or negative charge and behaves as a unit. The ammonium ion forms when a positively charged hydrogen ion, H+, attaches to the unshared electron pair of an ammonium molecule, NH3. Most plants need nitrogen that is already combined in a compound rather than molecular nitrogen N2 to grow. So here is an example of a polyatomic ion. Notice it said that the atoms respond as a unit. Each hydrogen and nitrogen has a noble gas configuration or an octet, be it neon for the nitrogen or helium for the hydrogen. So that is the ammonium polyatomic ion with a +1 charge. NH4, and then it's a plus charge. The fertilizer shown in figure 9 on the next page contains the nitrogen compound ammonium sulfate. Most polyatomic cations And anions contain both covalent and coordinate covalent bonds. Therefore, compounds containing polyatomic ions include both ionic and covalent bonding. As another example, draw the electron dot structure of the polyatomic ion SO3 sulfite -2 charge. Start by drawing the electron dot structures for the oxygen and sulfur atoms and the two extra electrons indicated by the charge. Then join two of the oxygens to sulfur by single covalent bonds. And what you'll end up doing is forming a molecule that has various kinds of bonds. The polyatomic ion, ammonium ion, NH4+1, present in ammonium sulfate, is an important component of fertilizer for field crops, home gardens, and potted plants. And on each bag of fertilizer, they'll give this series of numbers. And these numbers represent amounts of nitrogen is on the left, that's 18 for the one on the left, and then phosphorus 24, and potassium is 6. Or this other one is 26, 2, and 11, nitrogen, phosphorus, and potassium. But it's always standard to put nitrogen first, then phosphorus, then potassium. So if you look at any bag of fertilizer, it will have various numbers indicating that. So here is the sulfur, and so you have the sulfur and the three oxygens coming to form SO3, and you see those arrows. That's where the material's coming from, and you can see that coordinate bond between the sulfur and the oxygen on the right. So that's actually kind of a little interesting, and then so that gives you the polyatomic ion called sulfite, which has a -2 charge. Sulfate, SO4, also has a -2 charge. So you take sulfur trioxide plus that pair of electrons, and you form the sulfite ion, polyatomic ion. Then join the remaining oxygen by a coordinate covalent bond, with sulfur donating one of its unshared pairs to oxygen, and add the two extra electrons. Put brackets about the structure and indicate the -2 charge, giving the result shown. Each of the atoms of the completed structure has 8 valence electrons, satisfying the octet rule. Remember, I showed you there in the last in one of the slides where that oxygen came right in without electrons donating, and they were donating from sulfur. Without 2 extra electrons, 2 of the oxygens would be electron deficient. Table 2 lists electron dot structures of some common compounds with covalent bonds. So peruse that. We're going to be doing structures in class where you have to be able to predict the geometry of various structures and be able to build them from scratch. So we have hydrogen peroxide, sulfur dioxide, sulfur trioxide, nitric oxide, nitrogen dioxide, nitrous oxide, hydrogen cyanide, hydrogen fluoride, and hydrogen chloride. Remember, the electron dot structure for a neutral molecule contains the same number of electrons as the total number of valence electrons in the combining atoms. The negative charge of a polyatomic ion shows the number of electrons in addition to the valence electrons of the atoms present. Because a negatively charged polyatomic ion is part of an ionic compound, the positive charge of the cation of the compound balances these additional electrons. A large quantity of heat is released when hydrogen atoms combine to form hydrogen molecules. This suggests that the product is more stable than the reactants. The covalent bond in the hydrogen molecule H2 is so strong that it would take 435 kilojoules of energy to break apart all of the bonds in 1 mole, about 2 grams, of hydrogen gas, hydrogen H2. You will study the mole, abbreviated mole, MOL, in the chapter on stoichiometry and the chapter before stoichiometry. The energy required to break the bond between two covalently bonded atoms is known as the bond dissociation energy. The bond dissociation energy, that's what we're talking about. This is usually expressed as the energy needed to break 1 mole of bonds, or 6.02 times 10 to the 23rd bonds. The bond dissociation energy of H2 molecule is 435 kilojoules per mole. A large bond dissociation energy corresponds to a strong covalent bond. A typical carbon-carbon single bond has a bond dissociation energy of 347 kilojoules per mole. Typical carbon-carbon double and triple bonds have bond dissociation energies of 657 kilojoules per mole and 908 kilojoules per mole, respectively. Strong carbon-carbon bonds help explain the stability of carbon compounds. Very, very strong. Carbon with only C bond C or C bond H single covalent bonds, such as methane, tend to be quite unreactive. They are unreactive partly because the dissociation energy for each of these bonds is high. Let's say that again. Compounds with only a CC or CH single covalent bond, such as methane, tend to be quite unreactive. Ozone in the upper atmosphere blocks harmful ultraviolet radiation from the sun. At the lower elevations, shown in Figure 10, it contributes to smog. The ozone molecule has 2 possible electron dot structures. Notice that the structure on the left can be converted to the one on the right by shifting electron pairs without changing the position of oxygen atoms. As drawn, these electron dot structures suggest that the bonding in ozone consists of 1 single coordinate covalent bond and 1 double covalent bond. So this going back and forth is called resonance, and we'll look at that in a little bit. Although ozone high above the ground forms a protective layer that absorbs ultraviolet radiation from the sun, at lower elevations, ozone is a pollutant that contributes to smog. It is produced in the internal combustion engine. Ozone is a rather unpleasant side effect of using an internal combustion engine. And on the left and on the right, you can see terrible smog. I don't know where these pictures are from, but it's fairly nasty. In the United States, smog used to be a tremendous problem before they created laws governing the output of certain industry and emission regulations on cars. They need to do that in other countries as well. Because earlier chemists imagined that the electron pairs rapidly flip back and forth or resonate between the different electron dot structures, they used double-headed arrows to indicate that 2 or more structures are in resonance. Double covalent bonds are usually shorter than single bonds, so it was believed that the bond lengths in ozone were unequal. Experimental measurements show, however, that this is not the case. The 2 bonds in ozone are the same length. Ozone, again, is an example of resonating molecules, and this double bond will will change back and forth, the resonating electrons. So you have this kind of weird structure where the electrons go back and forth rather rapidly to form what some would consider two double bonds, but it's actually this going back and forth, creating this rather very stable molecule. It can be broken, but it's rather stable and unhealthy as well. This result can be explained if you assume that the actual bonding in the ozone molecule is the average of the two electron dot structures. The electron pairs do not actually resonate back and forth. The actual bonding of oxygen atoms in ozone is a hybrid or mixture of the extremes represented by the resonance forms. The two electron dot structures for ozone are examples of what are still referred to as resonance structures. A resonance structure is a structure that occurs when it is possible to draw two or more valid electron dot structures that have the same number of electron pairs for a molecule or ion. Resonance structures are simply a way to envision the bonding in certain molecules. Although no back and forth changes occur, double-headed arrows are used to connect resonance structures. Next. The Octet Rule provides guidance for drawing electron dot structures. For some molecules or ions, however, it is possible to draw structures that satisfy the Octet Rule. The Octet Rule cannot be satisfied in molecules whose total number of valence electrons is an odd number. There are also molecules in which an atom has fewer or more than a complete octet of valence electrons. The nitrogen dioxide NO2 molecule, for example, contains a total of 17, an odd number of valence electrons. Each oxygen contributes 6 electrons, and the nitrogen contributes 5. The nitrogen contributes 5, so that's for 17. Okay, so you have this resonance structure, or this fake kind of thing, but they call it resonance. And you have this flip-flopping back and forth where all the octets are satisfied. So it's called resonance, and it is just a way of kind of representing what really is going on with the electron distribution around the various atoms of the molecule. So here is the example where you have this double dotted line where you have this resonance going back and forth in the nitrogen dioxide molecule, the NO2. You can see that you are missing an electron for nitrogen. It only has 7. So if it weren't for this kind of flipping back and forth, you wouldn't be able to satisfy much. 2 plausible electron dot structures can be drawn for the nitrogen dioxide molecule. An unpaired electron, singular, is present in each of these structures, both of which fail to follow the octet rule. It is impossible to draw an electron dot structure for NO2 that satisfies the octet rule for all atoms. Yet, NO2 does exist as a stable molecule. In fact, it is produced naturally by lightning strikes of the sort shown in figure 11 on the next page. A number of other molecules also have an odd number of electrons. In these molecules, as in NO2, complete pairing of electrons is not possible. But it is naturally produced in the lightning, and lightning is one means by which the nitrogen and the oxygen in the atmosphere produce nitrogen dioxide. Here are several examples of lightning that will produce the nitrogen dioxide, this weird kind of molecule that we're talking about that shouldn't exist, but it does exist in nature. Lightning will produce it. it is not possible to draw an electron dot structure that satisfies the octet rule. Examples of such molecules include chlorine dioxide and nitric oxide, several molecules with an even number of valence electrons, such as some compounds of boron, also fail to follow the octet rule. This may happen because an atom acquires less than an octet of 8 electrons. The boron atom in boron trifluoride, for example, is deficient by 2 electrons and therefore is an exception to the octet rule. Though you will find other exceptions, aluminum trichloride, beryllium dichloride, you'll find several exceptions. Boron trifluoride readily reacts with ammonia to make the compound boron trifluoride ammonium. In doing so, the boron atom accepts the unshared pair from the unshared electron pair from ammonia and completes the octet. A few atoms, especially phosphorus and sulfur, sometimes expand the octet to include 10 or 12 electrons. Consider phosphorus trichloride and phosphorus pentachloride. Both are stable compounds in which all of the chlorines are bonded to a single phosphorus atom. You're also going to see xenon tetrafluoride, where you're going to have more than 8 electrons on the xenon. So there's going to be some weird stuff. Covalent bonding in phosphorus trichloride follows the octet rule because all the atoms have 8 valence electrons. However, as shown in figure 12 on the next page, the electron dot structures for phosphorus pentachloride can be written so that the phosphorus has 10 valence electrons. And as they say when the plot's about to thicken, the plot's about to thicken. Phosphorus pentachloride used as a chlorinating and dehydrating agent, and sulfur hexafluoride used as an insulator for electrical equipment are exceptions to the octet rule. Interpreting diagrams. How many valence electrons does the sulfur in sulfur hexafluoride, SF6, have for the structure shown in the figure? So this is going to be we're going to do a counting thing. And here we have the 2 molecules we're talking about, the sulfur hexafluoride and the phosphorus pentachloride, with the various bond angles and structural formulas. When we do our experiment on molecular geometry, these shapes will make more sense to you. So stay tuned for some molecular geometry. This car is being painted by a process called electrostatic spray painting. A custom designed spray nozzle wired up to an electric power supply imparts a negative charge to the paint droplets as they exit the spray gun. The negatively charged droplets are attracted to the auto body. Painting with attractive forces is very efficient because almost all the paint is applied to the car body and very little is wasted. In this section, you will learn how attractive and repulsive forces influence the shapes of molecules. Here is the car being sprayed, and this is how it's done. This is how the electrostatic paint is applied to this red car. See the guy in the mask there, and how you have a normal spray gun, and then you have the electrostatic spray gun, and the positively charged item, which in this case is the car, that is attracting these negatively charged particles and covering the car in a more efficient, effective manner. The model for covalent bonding you have been using assumes that the orbitals are those of the individual atoms. There is a quantum mechanical model of bonding, however, that describes the electrons in molecules using orbitals that exist only for groupings of atoms. When two atoms combine, this model assumes that their atomic models overlap to produce molecular orbitals, or orbitals that apply to the entire molecule. In some ways, atomic orbitals and molecular orbitals are similar, just as an atomic orbital belongs to a particular atom, a molecular orbital belongs to a molecule as a whole. So we're going to be studying molecular orbitals. Each atomic orbital is filled if it contains 2 electrons. Similarly, 2 electrons are required to fill a molecular orbital. A molecular orbital can be occupied by 2 electrons of a covalent bond, is called a bonding orbital. Sigma bonds, when 2 atomic orbitals combine to form a molecular orbital that is symmetrical around the axis connecting to atomic nuclei, a sigma bond is formed, as illustrated in figure 13 on the next page. The symbol for this bond is the Greek letter sigma, which is illustrated there, the sigma bond. 2 s atomic orbitals can combine to form a molecular orbital, as in the case of hydrogen. In a bonding molecular orbital, the electron density between the nuclei is high. That's going to be a probability. The probability is that it's very high between the 2 nuclei in terms of where it is, where its location is. To represent the nucleus, there you have the 2 s atomic orbitals, and that's forming the sigma bond, the molecular orbital for the sigma bond. Molecular orbitals, we're going to continue. It says, in general, covalent bonding results from an imbalance between the attractions and repulsions of the nuclei and electrons involved. Because their charges have opposite signs, the nuclei and electrons attract each other. Because their charges have the same sign, nuclei repel other nuclei and electrons repel other electrons. In a hydrogen molecule, the nuclei repel each other, as do the electrons. In a bonding molecular orbital of hydrogen, however, the attractions between the hydrogen nuclei and the electrons are stronger than the repulsions. Molecular orbital bonding. The balance of all the interactions between the hydrogen atoms is thus tipped in favor of holding the atoms together. The result is a stable diatomic molecule of H2, hydrogen gas, at room temperature. Atomic p orbitals can also overlap to form molecular orbitals. A fluorine atom, for example, has a half-filled 2p orbital. When 2 fluorine atoms combine, as shown in figure 14 on the next page, the p orbitals overlap to produce a bonding molecular orbital. There is a high probability of finding a pair of electrons between positively charged nuclei of the 2 fluorines. Figure 14, 2p atomic orbitals can combine to form a sigma bonding molecular orbital, as in the case of fluorine F2. Notice that the sigma bond is symmetrical around the bond axis, connecting the nuclei. So let's see what that means relative to F2, or fluorine gas at room temperature. Here is the plus sign represents the nucleus, and you have the p orbital, and it's around the nucleus, of course, and you're going to form the sigma bond. And that down below, it's kind of like locking in place. You're forming this sigma type structure. This sigma type structure, how it also locks in place. Here's another example of the molecular orbital theory with the anti-bonding and the bonding and the 2px and the 2px forming this kind of sigma bond, sigma 2p. It can get bonding can get very complicated. It's not as simple as they make out in the the elementary grades. It can get rather dicey. The fluorine nuclei are attracted to this region of high electron density. The attraction holds the atoms together in the fluorine molecule F2. Excuse me. The overlap of the 2p orbitals produces a bonding molecular orbital that is symmetrical when viewed around the F bond axis connecting the nuclei. Therefore, the F bond F bond is a sigma bond. Pi bonds in the sigma bond of the fluorine molecule, the p atomic orbitals overlap end to end in some molecules. However, orbitals can overlap side by side. As shown in figure 15 on the next page, the side-by-side overlap of atomic p orbitals produces what are called pi molecular orbitals. When a pi molecular orbital is filled with 2 electrons, a pi bond results. In a pi bond, symbolized by the Greek letter pi, the bonding electrons are most likely to be found in sausage-shaped regions above and below the bond axis of the bonded atoms. It is not symmetrical around the F bond axis. Atomic orbitals in pi bonding overlap less than in sigma bonding. Therefore, pi bonds tend to be weaker than sigma bonds. The side-by-side overlap of 2p atomic orbitals produces a pi bonding molecular orbital. Together, the 2 sausage-shaped regions in which the bonding electron pair is most likely to be found constitutes one pi bonding molecular orbital. So here are 2 side-by-side p orbitals, for instance the 2py and 2py, from 2 different elements forming this bond, and they're side by side, and they form this kind of like sausage or 2 pancakes up and down. It's a little bizarre. A photograph or sketch may fail to do justice to your appearance. Similarly, electron dot structures fail to reflect the 3-dimensional shapes of the molecules illustrated in figure 16 on the next page. The electron dot structure and structural formula of methane, for example, show the molecule as if it were flat and merely 2-dimensional. In reality, methane molecules are 3-dimensional. As figure 16a shows, the hydrogens in a methane molecule are at the 4 corners of a geometric solid called a regular tetrahedron. Methane and ammonia, represented here, are 3-dimensional molecules. Methane is a tetrahedral molecule. The hydrogens in methane are at the 4 corners of a regular tetrahedron, and the bond angles are all 109.5, close to that of water, and there's a reason for that. An ammonia molecule is pyramidal. The unshared pair of electrons repels the bonding pairs. Interpreting diagrams. How do the resulting H and H bond angles compare to the tetrahedral angles? Well, they should be 100 120 degrees, but they're out of the plane, so they're going to be somewhat less than 120 degrees, but not much. Here you have methane, this tetrahedron, and you have ammonia. Like I said, those bonds are forced out of the plane, so they're going to be less than 120, and actually less than the methane. But that's why they're 107. They should be 120, but that there's an unbonded pair of electrons above the nitrogen that forces them out of the arrangement. In this arrangement, all of the HCH angles are 109.5, the tetrahedral angle. The valence shell electron pair repulsion theory, Vesper theory, explains the three-dimensional shape of methane. According to Vesper theory, the repulsion between electron pairs causes molecular shapes to adjust to the valence electron pairs stay as far apart as possible. The methane molecule has 4 bonding electron pairs and no unshared pairs. The bonding pairs are farthest apart when the angle between the central carbon and its attracted hydrogens is 109.5. 109.5. This is the HCH bond angle found experimentally. Unshared pairs of electrons are also important in predicting the shapes of molecules. The nitrogen in ammonia is surrounded by 4 pairs of valence electrons. So you might predict the tetrahedral angle of 109.5 for the H and H bond angle. However, one of the valence electron pairs shown in figure 8.16b is an unshared pair. No bonding atom is vying for these unshared electrons. Thus, they are held closer to the nitrogen than are the bonded pairs. The unshared pair strongly repels the bonding pairs, pushing them together. The measured H and H bond angle is 107 degrees. In a water molecule, oxygen forms single covalent bonds with 2 hydrogen atoms. The 2 bonding pairs and the 2 unshared pairs of electrons form a tetrahedral arrangement around the central oxygen. Thus, the water molecule is planar, flat, but bent, with 2 unshared pairs repelling the bonding pairs. The HOH bond angle is compressed in comparison with the HCH bond angle in methane. So it gets kind of complicated. The experimentally measured bond angle in water is about 105 degrees, as shown in figure 17a on the next page. In contrast, the carbon in the carbon dioxide molecule has no unshared electron pairs. The double bond joins the oxygens to the carbon are the farthest apart when the O double bond C double bond O bond angle is 180 degrees, as illustrated in figure 17b. Thus, CO2 is a linear molecule. Figure 17, this comparison of water and carbon dioxide illustrates how unshared pairs of electrons can affect the shape of a molecule made of 3 atoms. The water molecule is bent because the 2 unshared pairs of electrons on oxygen repel the bonding electrons. In contrast, the carbon dioxide molecule is linear. The carbon atom has no unshared electron pairs. So A, the water molecule is bent because the 2 unshared pairs of electrons on the oxygen repel the bonding electrons, and B, in contrast, the carbon dioxide molecule is linear. The carbon atom has no unshared electron pairs. So it's the absence of the unshared pair of electrons that will make the difference. So here is carbon dioxide and water. One has this rather complicated looking, almost tetrahedral quality to it. Although it's not 109.5, it's pretty close in terms of the 4 pairs of electrons that are around it. That's why it kind of simulates diamond. Diamonds are, when the carbons are related to each other tetrahedrally, and then the carbon dioxide is linear. 9 of the possible molecular shapes are shown in figure 18 on the next page. The VSEPR theory works well when accounting for molecular shapes, but it does not help much in describing the types of bonds formed. Orbital hybridization provides information about both molecular bonding and molecular shape. In hybridization, several atomic orbitals mix to form the same total number of equivalent hybrid orbitals. Okay, figure 18 shown here are common molecular shapes. These are the molecular shapes that we will be examining in the lab on molecular geometry. You have the diatomic, where it's just simply linear, obviously. Linear, bent. These are the different, we're going to be looking at these. Linear, we have additional ones where it is a little bit more complex, where you have you see the E3, that means how many unshared pairs of electrons there are. So, and then you have the Trigonal Planar, where you have no excess electrons, the yellow being the excess electrons. Then the Trigonal Pyramid, the T-shape, where you have AX3E2. Then you have the tetrahedral, where you have no unshared pairs of electrons. And then continuing with a couple of more slides, you can see here's another look at it, the different types of geometry relative to linear, bent, trigonal planar, and trigonal pyramidal, and we'll continue with the next slide. And now here we have the square planar, the tetrahedral, again, the trigonal bipyramidal, and the octahedral. So you're going to be rather busy doing this molecular geometry experiment. Hybridization involving single bonds. Recall that the carbon atom's outer electron configuration is 2s2, 2p2, but one of the 2s electrons is promoted to a 2p orbital to give one 2s electron and 3 2p electrons, allowing it to bond to 4 hydrogen atoms in methane. You might suspect that one bond would be different from the other 3. In fact, all the bonds are identical. This is explained by orbital hybridization. The 1 2s orbital and 3 2p orbitals of a carbon atom mix to form 4 sp3 hybrid orbitals. That's 4 sp3 hybrid orbitals. These are the tetrahedral, these are at the tetrahedral angle of 109.5. As you can see in figure 19 of the next page, the 4 sp3 orbitals of carbon overlap with the 1s orbitals of the 4 hydrogen bonds, the 4 hydrogen atoms. The sp3 orbitals extend farther into space than either s or p orbitals, allowing a great deal of overlap with the hydrogen 1s orbitals. The 8 available valence electrons fill the molecular orbitals to form 4 CH sigma bonds. The extent of overlap results in unusually strong covalent bonds. Figure 19, in methane, each of the 4 sp3 hybrid orbitals of carbon overlaps with a 1s orbital of hydrogen. Okay, Here we have the atomic orbitals of two hydrogen atoms, and then you have the hybrid orbitals of the carbon atom. They are going to overlap and form these four sigma bonds of the methane molecule, creating four very stable bonds. It just so happens that the oxygen will readily combine with methane, but the bonds are stable. Hybridization involving double bonds. Hybridization is also useful in describing double covalent bonds. Ethene is a relatively simple molecule that has one carbon-to-carbon double bond and four carbon-hydrogen single bonds. Experimental evidence indicates that the HCH bond angles in ethene are about 120 degrees. In ethene, sp2 hybrid orbitals form from the combination of 1 2s and 2 2p atomic orbitals of carbon, as you can see in figure 20 on the next page. Each hybrid orbital is separated from the other two by 120 degrees. Two sp2 hybrid orbitals of each carbon form sigma bonding molecular orbitals with the four available hydrogen 1s orbitals. The third sp2 orbitals of each of the two carbons overlap to form a carbon-to-carbon sigma bonding orbital, single bonding orbital. In figure 20, in an ethene molecule, two sp2 hybrid orbitals from each carbon overlap with a 1s orbital of hydrogen to form a sigma bond. The other sp2 orbitals overlap to form a carbon-carbon sigma bond. The p atomic orbitals overlap to form a pi bond. Interfering, what region of space does a pi bond occupy relative to the carbon atoms? Relative to the carbon atoms. And that's a question. What region of space does a pi bond occupy relative to carbon atoms? So, here is the ethene molecule where you have this rather complex combination of sigma bonds and pi bonds, and you see the sigma bonds bonding, and then you have this one sigma bond, and then you have the pi bond, the overlapping ones coming in. They're both horizontal, and then you have the side by side. And here are some ball and stick models of ethene and ethine. Ethine is acetylene, and that's a triple bond that forms between the two carbon atoms. So it's going to be two single bonds with the hydrogen carbon and then a triple bond between the two carbons, and that's ethine or acetylene. Very, very explosive material when combined with water. When the calcium carbide is combined with water, it forms ethine, acetylene, which is very explosive. The non-hybridized 2p carbon orbitals overlap side by side to form a pi bonding orbital. A total of 12 electrons fill 6 bonding molecular orbitals. Thus, 5 sigma bonds and 1 pi bond hold the ethene molecule together. The sigma bonds and the pi bond are two electron covalent bonds. Although they are drawn alike in structural formulas, pi bonds are weaker than the corresponding sigma bonds. They are weaker. So the sigma bonds are stronger bonds, such as those in methane. In chemical reactions that involve breaking one bond of a carbon-to-carbon double bond, the pi bond is more likely to break than the sigma bond. Hybridization involving triple bonds. A third type of covalent bond is a triple bond, which is found in ethine, C2H2, also called acetylene, as the other molecules, as with other molecules, the hybrid orbital description of ethane is guided by an understanding of the properties of the molecule. As with other molecules, the hybrid orbital description of the ethane is guided by an understanding of the properties of the molecule. Ethane is a linear molecule. The best hybrid orbital description is obtained if a 2s atomic orbital of carbon mixes with only one of the three 2p atomic orbitals. The result is 2 sp hybrid orbitals for each carbon. The carbon-carbon sigma bonding molecular orbital of ethane molecules is in figure 21 on the next page. Forms from the overlap of one sp orbital from each carbon. The carbon-carbon sigma bonding molecular orbital of the ethane molecule. Figure 21, in an ethane molecule, one sp hybrid orbital from each carbon overlaps with a 1s orbital of hydrogen to form a sigma bond. The other sp orbital, a hybrid orbital, of each carbon overlaps to form a carbon-carbon sigma bond. The 2p atomic orbitals from each carbon also overlap. Interpreting diagrams. How many pi bonds are formed in an ethane molecule? All right, this is kind of funky looking. This is, you have the two hydrogens on the left and the right up top, and then you have the carbon with the sp hybridization. Now you're going to have the two sigma bonds bond with either hydrogen on either side, and then you're going to form this kind of two kind of funky pi bonds, and you're going to form this triple bond where you have two pi bonds and that sigma bond. The other sp orbital of each carbon overlaps with the 1s orbital of each hydrogen, also forming sigma bonding molecular orbitals. The remaining pair of p atomic orbitals on each carbon overlap side by side. They form two pi bonding molecular orbitals that surround the central carbons. The 10 available electrons completely fill 5 bonding molecular orbitals. The bonding of ethane consists of 3 sigma bonds and 2 pi bonds. That's a sigma bond, carbon to carbon, 2 carbon to hydrogen bonds, those are sigma bonds. Then you have 1 sigma bond for the carbon to carbon, and then the 2 pi bonds to complete the triple bond between the 2 carbons. Snow covers approximately 23% of the Earth's surface. Each individual snowflake is formed from as many as 100 snow crystals. The size and shape of each crystal depends mainly on the air temperature and amount of water vapor in the air at the time the snow crystal forms. In this section, you will see that the polar bonds in water molecules influence the distinctive geometry of snowflakes. And here are some rather beautiful snowflakes. You see that kind of hexagonal shape in each of the snowflakes. It's a very common shape, obviously, among snowflakes for various reasons because of water. You also see it several other places in nature, but the snowflakes are quite beautiful, and they all have this hexagonal structure, every one of them. Bond polarity. Covalent bonds involve electron sharing between atoms. However, covalent bonds differ in terms of how the bonded atoms share the electrons. The character of the bonds in a given molecule depends on the kind and number of atoms joined together. These features in turn determine the molecular properties. The bonding pairs of electrons in covalent bonds are pulled, as in the tug-of-war in figure 22 on the next page, between the nuclei of the atoms sharing the electrons. Figure 22, the nuclei of atoms pull on the shared electrons, much as the knot in the rope is pulled toward opposing sides in a tug-of-war, as shown in the following slide. And here is a tug-of-war, and you have the two nuclei and this dipole moment, and so you have this kind of bond polarity, which will create a molecular polarity, or it may not. It may cancel it out. When the atoms in a bond pull equally, as occurs when identical atoms are bonded, the bonding electrons are shared equally, and the bond is a nonpolar covalent bond. Molecules of hydrogen, oxygen, and nitrogen have nonpolar covalent bonds. Diatomic halogen molecules such as chlorine are also nonpolar. A polar covalent bond, known as a polar bond, is a covalent bond between atoms in which the electrons are shared unequally. The more electronegative atom attracts electrons more strongly and gains a slightly negative charge. Here are some examples of that, where you have this kind of unequal sharing and you create this dipole. So where you have hydrogen and chlorine, hydrogen chloride, you have this dipole to the right, and you have this hydrogen and oxygen, water, down below, where you have this dipole going up because the oxygen is more electronegative. You're going to need an electronegativity table with you in order to do bond polarity. The less electronegative atom has a slightly positive charge. Refer back to Table 2 in Chapter 6 to see the electronegativities of some common elements. The higher the electronegativity value, the greater the ability of an atom to attract electrons to itself. Consider the hydrogen chloride molecule HCl, shown in Figure 23 on the next page. Hydrogen has an electronegativity of 2.1 and chlorine 3. These values are significantly different, so the covalent bond in hydrogen chloride will be and is polar. Figure 23, this electron cloud picture of hydrogen chloride shows that the chlorine atom attracts the electron cloud more than the hydrogen atom does, inferring which atom is more electronegative, a chlorine atom or a hydrogen atom, apart from the fact that it just said that chlorine is 3 and hydrogen is 2.1, so obviously it would be chlorine would be the more electronegative element in the compound or the molecule hydrogen chloride in gaseous state. And here's the picture of the hydrogen chloride. So the shift, the dipole, is going to be towards the chlorine, and there's the nucleus of each, and that's hydrogen chloride. And it's going to be polar. The bond is polar because it's going towards the chlorine. Here is a table, Table 2 from Chapter 6, which shows the electronegativities of elements, where fluorine is 4, that's high, and it decreases diagonally across to cesium, which is 0.7. Francium is also very low, that's below that. And here are some compounds, some molecules, hydrogen chloride, polar, and you have this unbalanced shift in the dipoles. So ammonia would be polar, and then the boron trifluoride is nonpolar, and then the carbon tetrachloride is nonpolar, and the chlorinated carbon, where you have chlorine on one side and then the three hydrogens, that would be polar because you have an unbalanced dipole that's running vertically there, as you can see. The chlorine atom acquires a slightly negative charge. The hydrogen atom acquires a slightly positive charge. The lowercase Greek letter delta denotes the atoms involved in the covalent bond acquire only partial charges, less than one, or 1. The minus sign in this notation shows that chlorine has acquired a slightly negative charge. The plus sign shows that hydrogen has acquired a slightly positive charge. These partial charges are shown as clouds of electron density. The polar nature of the bond may also be represented by an arrow pointing to the more electronegative atom, as shown here. The OH bonds in the water molecule are also polar. The highly electronegative oxygen partially pulls the bonding electrons away from hydrogen. The oxygen acquires a slightly negative charge. The hydrogen is left with a single positive charge, as shown in Table 3 on the next page. The electronegativity difference between two atoms tells you what kind of bond is likely to form. Remember, when you use the table, that there is no sharp boundary between ionic and covalent bonds. So the greater the difference in electronegativity, the more polar or ionic the bond will be. And the less the difference, as in hydrogen-hydrogen, where it's the same, it would be completely and absolutely covalent. So here's the electronegativity difference and whether or not something is ionic or covalent or very polar covalent, etc. So that's the table that tells you whether or not something's going to be ionic or covalent. Very, very important distinction between the two. So very polar covalent is not ionic, but it's certainly, it's certainly covalent, but the shift is very strong. As the electronegativity difference between two atoms increases, the polarity of the bond increases. If the electronegativity difference is greater than 2, it is very likely that electrons will be pulled away completely by one of the atoms. In that case, an ionic bond will form. So here are some compounds where you have a dipole moment of 0. Everything's canceled on the first one. That's methane. Ammonia, the dipole moment 4.6 D. Then water, 1.87 D. The dipole moment of the fluorine, hydrogen fluoride, is 1.83 D. And then the carbon dioxide has none, and sulfur trioxide has none. The presence of a polar bond in a molecule often makes the entire molecule polar. In a polar molecule, one end of the molecule is slightly negative and the other end is slightly positive. In the hydrogen chloride molecule, for example, the partial charges on the hydrogen and chlorine atoms are electrically charged regions or poles. A molecule that has two poles is called a dipolar molecule or dipole. The hydrogen chloride molecule is a dipole. Look at figure 24 on the next slide. So this whole concept of dipole means it has two poles. If something's polar, it has poles, but dipole means specifically two poles. When polar molecules such as hydrogen chloride are placed in an electric field, the slightly negative ends of the molecules become oriented towards the positively charged plate, and the slightly positive ends of the molecules become oriented towards the negatively charged plate, predicting what would happen if instead carbon dioxide molecules were placed between the plates and why. Here I have some examples of these polar molecules lining up between two electric plates in an electric field, and where you have the electric field is off versus the electric field is on, and you have the positive is attracted to the negative plate, and the negative side is attracted to the positive plate, etc. Here we have hydrogen chloride lining up, same thing as the other ones. Here I have another molecule with an obvious net dipole lining up appropriately, positive and negative. Here I have carbon dioxide is nonpolar, and then I have water that is polar. The carbon dioxide, they cancel, and you have a net dipole with water. When polar molecules are placed between oppositely charged plates, they tend to become oriented with respect to the positive and negative plates, as we just saw. The effect of polar bonds on the polarity of an entire molecule depends on the shape of the molecule and the orientation of the polar bonds. A carbon dioxide molecule, for example, has two polar bonds and is linear. Note that the carbon and oxygens lie along the same axis. They're all linear, so they're all along the same axis. Therefore, the bond polarities cancel because they are in opposite directions. Carbon dioxide is thus a nonpolar molecule despite the presence of two polar bonds. The water molecule has two polar bonds. However, the water molecule is bent rather than linear, therefore the bond polarities do not cancel and the water molecule is polar. One of the reasons they don't cancel is because you have that unshared pair of electrons. Molecules can attract each other by a variety of forces. Intermolecular attractions are weaker than either ionic or covalent bonds. Nevertheless, you should not underestimate the importance of these forces. Among other things, these attractions are responsible for determining whether a molecular compound is a gas or a liquid or a solid at a given temperature. Van der Waals forces, the two weakest attractions between molecules, are collectively called van der Waals forces, named after the Dutch chemist Johann van der Waals, 1837 to 1923. Johannes van der Waals. Van der Waals forces consist of dipole interactions and dispersion forces. Dipole interactions occur when polar molecules are attracted to one another. The electrical attraction involved occurs between the oppositely charged regions of polar molecules as shown in figure 25 on the next page. The slightly negative region of a polar molecule is weakly attracted to the slightly positive region of another polar molecule. Dipole interactions are similar to, but much weaker than, ionic bonds. We will study van der Waals forces very, very thoroughly in chapter 15 when we talk about water. Polar molecules are attracted to one another by dipole interactions, a type of van der Waals forces. This is figure 25. Here are some examples of this dipole interaction where you have this attraction as a result of these partial charges that are set up within the molecules, such as in hydrogen bonding, but that's a little bit stronger. Roughly spherical atoms of an ideal gas should not be attracted nor repelled by one another. Those are gases. When we talk about ideal gas laws, we'll talk more about that. A real gas atom can have an instantaneous dipole. Partial charges on one atom cause a neighboring atom to distort due to the electrostatic attraction repulsion of their electron clouds. Attractions between opposite partial charges of neighboring induced dipoles cause atoms to stick together for a very short time. So again, you're going to have these dipole attractions between molecules that have these slight dipoles, net dipoles that are in them. These internal dipoles. Here you have the repulsion of the dipole. So it's rather complex, and it's just an introduction for now, but it will become much more difficult as the year progresses. Dispersion forces, the weakest of all molecular interactions, are caused by the motion of electrons. They occur even between nonpolar molecules. When the moving electrons happen to be momentarily more on the side of a molecule closest to a neighboring molecule, their electric force influences the neighboring molecule's electrons to be momentarily more on the opposite side. This causes an attraction between the two molecules similar to, but much weaker than, the force between permanently polar molecules. These forces, these dispersion forces, causes matter to have unpredictable properties, and we will study it in great detail in the coming chapters. The strength of dispersion forces generally increases as the number of electrons in a molecule increases. The halogen diatomic molecule, for example, attract each other mainly by means of dispersion forces. Chlorine and fluorine have relatively few electrons and are gases at ordinary room temperature and pressure because of their especially weak dispersion forces. The larger number of electrons in bromine generates larger dispersion forces. And bromine is going to be a liquid gas at room temperature. It's a little bit more of a liquid. That's when it approximately changes. Bromine molecules therefore attract each other sufficiently to make bromine a liquid at ordinary room temperatures, barely, and pressure. Iodine, with a still larger number of electrons, is a solid at ordinary room temperature and pressure. Hydrogen bonds, the dipole interaction in water, produce an attraction between water molecules. Each OH bond in the water molecule is highly polar, and the oxygen acquires a slightly negative charge because of its greater electronegativity. The hydrogens in water molecules acquire a slightly positive charge. This gives water an unusual property, or unusual set of properties. It makes life possible on Earth. Not to sound too dramatic, but it's quite true. The positive region of one water molecule attracts the negative region of another water molecule, as illustrated in Figure 26. This attraction between the hydrogen of one water molecule and the oxygen of another water molecule is strong compared to the other dipole interactions. This relatively strong attraction, which is also found in hydrogen containing molecules other than water, is called a hydrogen bond. Figure 26 on the next page illustrates hydrogen bonding in water. The property of being able to float when it gets colder, it expands, is a particular property of hydrogen bonding. Many of the properties, unusual properties of water, water shouldn't act the way it does, but it does because of this hydrogen bonding. The strong hydrogen bonding between water molecules accounts for many properties of water, such as the fact that water is a liquid rather than a gas at room temperature. In ammonia, with the electronegative atom must have one or more unshared electron pairs, as in the case of oxygen and nitrogen, and has a negative partial charge. The hydrogen, which has a partial positive charge, tries to find another atom of oxygen or nitrogen with excess electrons to share and is attracted to the partial negative charge. This forms the basis for the hydrogen bond. The hydrogen on one molecule attached to oxygen or nitrogen that is attracted to an oxygen or nitrogen of a different molecule. Some combinations which are not hydrogen bonds include hydrogen to another hydrogen or hydrogen to a carbon. Here is an example of the hydrogen bonding in different types of molecules. Here in the upper left is water, and down below is a particular type of organic substance. On the right, you have methanol, where you have this hydrogen bond with the between the oxygen and the hydrogen. So here's another example of hydrogen bonding and the length of the hydrogen bond. And again, water has many unusual properties because of this hydrogen bonding. On the left, it says some combinations which are not hydrogen bonds include hydrogen to another hydrogen or hydrogen to a carbon. Now, ammonia with hydrogen bonding. The electronegative atom must have one or more unshared electron pairs, as in the case of oxygen and nitrogen, and has a negative partial charge. The hydrogen, which has a partial positive charge, tries to find another atom of oxygen or nitrogen with excess electrons to share and is attracted to the partial negative charge. This forms the basis for a hydrogen bond. The hydrogen on one molecule attached to oxygen or nitrogen that is attracted to an oxygen or nitrogen of a different molecule. Again, hydrogen bonding. We will emphasize this in the entire book. Hydrogen bonds are attractive forces in which a hydrogen covalently bonded to a very electronegative atom is also weakly bonded to an unshared electron pair of another electronegative atom. This other atom may be in the same molecule or in a nearby molecule. It's called hydrogen bonding. Hydrogen bonding always involves hydrogen. It is the only chemical reactive element with valence electrons that are not shielded from the nucleus by other electrons. Remember that for a hydrogen bond to form, a covalent bond must already exist between a hydrogen atom and a highly electronegative atom, such as oxygen, nitrogen, or fluorine. The combination of this strongly polar bond and the lack of shielding effect in a hydrogen atom is responsible for the relative strength of hydrogen bonds. Hydrogen bonding, I cannot emphasize more, is a very important aspect of chemistry. A hydrogen bond has about 5% of the strength of an average covalent bond. Hydrogen bonds are the strongest of the intermolecular forces. In other words, those what we might call physical bonds. They are extremely important in determining the properties of water and biological molecules such as proteins. Figure 27 on the next page shows how the relatively strong attractive forces between water molecules cause the water to form small droplets on a waxy surface. The beating up of water is an example of hydrogen bonding at work. Hydrogen bonding explains a lot of the behavior of water. Figure 27, the strong attractions between water molecules cause the water to pull together into small drops rather than spread over the surface of the flower. When you put in a surfactant into laundry, or detergents contain surfactants, the surfactant is to reduce hydrogen bonding. That's what the surfactants do. It gets rid of the bubbling. And here we have this kind of bubbling up, this beating up of water on flowers or on tree stems. Here's you have a little ant that's the size of the bead of water, and these beads of water occur because of the hydrogen bonding in water. Wrinkling in clothes is a result of hydrogen bonding. Hydrogen bonding is all over the place. The garment industry spends millions of dollars annually to get rid of hydrogen bonding, or to make clothes that are resistant to hydrogen bonding. All of these flowers are where the water is beating is a result of hydrogen bonding. Here is a rose with some beating of water. Again, hydrogen bonding. How many properties can you think of that are caused from hydrogen bonding relative to water? Intermolecular attractions and molecular properties at room temperature. Some compounds are gases, some are liquids, and some are solids. The physical properties of a compound depend on the type of bonding it displays, in particular on whether it is ionic or covalent. The great range of physical properties occurs among covalent compounds. This is mainly because of widely varying intermolecular attractions. We will spend an entire chapter later on in the year on this topic. The melting and boiling points of most compounds composed of molecules are low compared with those of ionic compounds. In most solids formed from molecules, only the weak attractions between molecules need to be broken. However, a few solids that consist of molecules do not melt until the temperature reaches 1,000 degrees Celsius or higher, or they decompose without melting at all. Most of these very stable substances are network solids or network crystals, solids in which all of the atoms are covalently bonded to each other. Melting a network solid would require breaking covalent bonds throughout the solid. Diamond is an example of a network solid. As shown in Figure 28, each carbon atom in a diamond is covalently bonded to 4 other carbons, interconnecting carbon atoms throughout the diamond. Cutting a diamond requires breaking a multitude of these bonds. Diamond does not melt, rather it vaporizes to a gas at 3,500 degrees Celsius and above. Silicon carbide with the formula SiC and a melting point of about 2,700 degrees Celsius is also a network solid, as well as silicon oxide, which is sand. Diamond is a network solid form of carbon. Diamond has a 3-dimensional structure with each carbon at the center of a tetrahedron. Each carbon at the center of a tetrahedron. Here is a slide with 3 examples: silicon oxide, graphite used as a lubricant, and diamond. Silicon carbide is so hard that it is used in grindstones and as an abrasive, as illustrated in Figure 29. The molecular structures of silicon carbide and diamond are similar to each other. You can think of samples of diamond. silicon carbide, and other network solids as single molecules. That's very important, single molecules. Silicon carbide, a network solid, is so hard that it is used in this grindstone to wear down the end of a hardened steel cutting tool to form a sharp edge. So it can be used as a grinder because of its great durability and strength. Here is an example of the grinder that the person is using on the steel cutting instrument. And you can also see how it can be used to etch glass. The silicon carbide tools can be used to make beautiful glass etchings. Here are some examples of the silicon carbide. The Porsche Carrera GT's carbon ceramic disc brakes, a piece of silicon carbide used in steel making, and grinding wheel silicon carbide. These are all applications of this rather durable substance called silicon carbide, or SiC. Table 8.4 summarizes some of the characteristic differences between ionic and covalent molecular substances. Note that ionic compounds have higher melting points than molecular compounds. Ionic compounds also tend to be soluble in water. Those are just two of the differences between ionic and covalent substances. Table 8.4 will become very important as we proceed with chemistry. So there's table 4. You should look it over, be very familiar with it, be able to answer questions relative to the differences and the similarities between ionic and covalent substances. The chemistry of adhesives. Most common adhesives are sticky substances that you can use to bind two surfaces together. The diagram on the next page shows how some adhesives work. The adhesive is a liquid until the surfaces are in position. Then the adhesive sets into a solid. Adhesion can work in 3 ways. Molecules of the polymer may fill crevices in the surfaces being connected. The molecules may become attracted by intermolecular forces, or they may react by forming covalent bonds. Interpreting diagrams explain the purpose of the stabilizers in an adhesive. Okay, number 1, a liquid adhesive. In a typical adhesive, monomer molecules and a stabilizer are in a solvent. The stabilizer stops the monomer from forming a solid polymer. Number 2, applying the adhesive. Squeezing the tube releases the liquid onto one of the surfaces to be joined. Part 3, setting the adhesive. Contact with water in the air and on the surfaces being joined makes the stabilizer inactive. The monomers then begin to join together to form polymers. As the chain lengthens, the adhesive changes from a liquid to a solid. The little postums, temporary adhesion. The sticky strip on a reusable note is a microsphere adhesive. The microspheres limit the amount of surface area contact, so the paper sticks lightly and repositions easily. Well, that concludes the lecture on bonding, chapters 7 and 8. Here are some of the resources that were used, some of the many resources that were used to come up with this lecture. Have a great day and Goodbye.